So let's get started. Welcome to day 4. And as usual, I start my presentations with a warning. Working in this field, even being interested in this field, can and will destroy your career, personal and professional life as well. So what have we done so far? We've actually done a lot. We've been interested in the Fleischman-Pons experiment, trying to understand it from the point of view of conventional physical chemistry, applied physics, electrochemistry, thermodynamics. We've got an idea of what it is that the experiment's doing. And we discussed earlier making vacancies to get places with reduced electron density so we can get the molecule. We talked about observations of helium-4 in amounts commensurate with the energy. So we have experimental observations of a product, time correlation with excess power. We have excess energy to helium-4 ratio observations of it from experiment near 24 MeV, which is important because 24 MeV is the mass difference between two deuterons and a helium-4. At issue is to figure out what the energy of the helium-4 is when it's born. And for that we need a detector. We decided that palladium deuteride itself could be our detector. And once we calibrated and looked at the data, we found that the helium-4, the alpha particle, is born basically stationary. It's the neutron measurements are consistent with the helium-4 being born with no kinetic energy at all. The upper limit's 20 kilovolts with a reaction Q somewhere in the neighborhood of 24 MeV. That's less than 1/10 of 1% of the reaction energy. And that's very unusual. There's no reasonable Rutherford picture reaction scenarios for that. Of the 1,000 or more papers on theoretical approaches to understanding cold fusion, the large majority are inconsistent with this inference from the neutron measurements. Okay, so we want to begin taking the next step or two. The next step or two, if you like, we said on Monday that the existence of Fleischman-Pons effect is in contradiction to condensed matter physics and nuclear physics. And slowly we've been taking step by step trying to understand the experiment. Today, our steps are going to lead us to confront condensed matter physics and nuclear physics before the day is over. But we're going to be dragged there kicking and screaming. We would like not to bump up against condensed matter physics and nuclear physics, but there's going to ultimately be no alternative. The place we're going to start is with the two laser experiment. So given this situation, we're interested in the issue of what's going on. We have lots and lots and lots of energy. We have no commensurate chemical reaction products. We have commensurate helium-4 observed correlated with the excess power. We've got a Q value which in two measurements is consistent but does not prove D plus D going to helium-4. We have no commensurate nuclear radiation. We have helium-4 born at rest. We have no plausible Rutherford picture. And in a sense, what we lost by having no energetic nuclear reaction products is we lost the Rutherford picture. And that's a gigantic thing to lose. A Rutherford picture reaction would have been much preferred because we could have understood simply what's going on. But if you like, we respect experiment. We respect experimental results. You have a new effect. You have two approaches. One, you could say, well, I know from other experiments how it has to work, in which case you can say it can't work so the experimentalists are clowns. Or you can say, let's look at the experimental data, let's look at the experiments and see what the experiment's telling us. And from that, see if we can scratch our heads and figure out what's going on. And from my perspective, the question is where does the energy go? If, for example, on the TV programs and the mysteries, how do you solve a crime? Follow the money. Well, in a physics mystery, how do you solve a physics mystery? Follow the energy. Always get you to the right answers to what's going on and how things work.
Quick question. What do you have to say about claims of hydrogen fusion or other things? Do you think it's strictly DD fusion, which is going on in these experiments? There's no other types of fusion?
There are other types of fusion, and if you like, you're getting ahead of the story. Tomorrow, we're going to be interested in other things. Today, we're sort of taking baby steps. The Pons Fleischmans with heavy waters with deuterium in the lattice. Helium-4 is measured, so we're thinking 2Ds may be going to helium-4 and trying to take baby steps to figure that out. There certainly are light water experiments. Mitchell's talked about some of them, and there's certainly be discussed in the literature. And we're going to think about that tomorrow. Okay, so the question is what in the world is nature up to? So suppose we're thinking about D plus D going to helium-4. We've got 24 MeV roughly of excess energy, or energy mass difference being converted to energy. In a low energy nuclear collision, we get a 24 MeV gamma. We presented data for that. It's been observed with the sodium iodide detectors. The conjecture that's been made over the years, over many years, is maybe something different happens in the condensed matter environment. Now, the arguments for that so far are tremendously weak, and to even suggest such a thing is likely to get you invited to an auto-da-fe in this day and age. However, we don't see the gammas. We don't see any kind of energetic nuclear radiation. So we are forced, kicking and screaming, to contemplate the notion that maybe the energy is going into solid state degrees of freedom. This is not a position where we would like to be. On the other hand, there are not very many places energy can go. And so as a result, to clarify this, we need to go back to experiment. Sadly, we're not yet in a position we can rely on theory to sort this out. We need to go back to observations to see what does nature think about these ideas. And the place where we're going to end up is the 2-laser experiment, but before we get to the 2-laser experiment, we're interested in the 1-laser experiment. So in experiments more than a decade ago, in essence, Dennis Cravens, actually much earlier, was interested in excess heat experiments and wondering what it would respond to. And, well, suppose we apply some RF, suppose we take a laser pointer, shine a laser pointer at the experiment, what does it do? And what was observed is shining a laser pointer at the experiment could actually stimulate excess heat. And this is completely unexpected. So the basic idea is that if you take a Fleischman-Pons experiment and if you think of it, if you think of the experiment, you can run it in a way that produces excess heat, and then imagine backing it down. You say, well, how do you back it down? If you turn the electric current, chemical current down, you're backing it down. If you lower the temperature, you're backing it down. So if you set the thing just under threshold for turning it on, and then you shine a laser on, in this case, here's an early example of a single laser experiment. Systems operating, a red laser gets turned on, shines on the surface here, and an excess heat event is initiated. The amount of excess heat in these experiments tends to be more than an order of magnitude higher than the laser power. In some cases, 2 orders magnitude higher than the absorbed laser power. Here's another example. Once the 2 Dennises explained to people what they were seeing, everyone was interested. So there were quite a few experiments to try to see if the effect could be replicated. So here was one that was done at SRI. And this is a complicated graph, and I'm not sure I'm going to be able to explain everything to you, but I can point to one piece of it which might be of interest. So I'm looking at this curve right here, and this curve, there's some ramps. And these ramps have something to do with the change in temperature applied to the laser, so the laser gets tuned, so it's sweeping across a narrow band of frequencies in the red. So if you like, at this point, there's no laser on. At this point, there's either no or little excess heat. In this case, there's a little bit of excess heat. Now the laser turns on, the excess heat burst turns on. The laser scanning across different frequencies, so the excess heat maybe is responding to different frequencies, maybe it's not responding to different frequencies, maybe it's just a lag. And now when the laser turns off, the excess heat turns off. And this is, well, this is interesting, and it's interesting for a lot of reasons. It's interesting here from our point of view because you've got control over the excess heat. You can turn the laser on, bing, excess heat turns on, you turn the laser off, bing, it goes down. And if you like, there's a number of examples of that kind of effect happening here. It's not perfect, and you can argue one way or another, but that's the essential experimental result, that the kind of thing was seen in a number of laboratories. So in this particular case, you've got Fleischman Pons cell. In Letz's protocol, you add a little bit of gold on the surface. Why gold? What's special about gold? Well, gold has a plasmon resonance, which if it goes down a thin film, happens to be reasonably well matched to the red laser light that Dennis is using. Whether that's important or not has not been clarified in experiment. But laser excitation at a few milliwatt level appears to be able to turn on 50, 100, or 200 milliwatt thermal response. Now, when we saw those results, we were amazed. And I was thinking in the quantum optics business, people will sometimes use two lasers. They'll do experiments with two lasers. And the idea is that oftentimes the system will respond to the frequency difference between the two lasers. So the idea is that I've been very interested in vibrations. So I said to Dennis, I said, well, if one laser can work, suppose you try two lasers and you change the frequency. And you know, Dennis has been around the block before, and he's worked with the theorists before, and he knows that theorists in generally are a squirrely bunch. So he said, okay, so if I do this, what's your prediction as to what's going to happen? And of course, you know, your normal theorist is one that says, well, something's going to happen, it might do this, it might do that. I'm unsure because certainty. Dennis, of course, didn't put up with it. He said, write it down, put it down in black and white. What frequencies should we hit? You know, what do you expect to happen? And so I said, well, hit the gamma point for the optical phonon nodes. There's the little gamma point. What's the gamma point? 8.5 terahertz. That's where it is, trying to the 8.5 terahertz. And he says, okay, well, where else? I said, well, there's another compressional point where the group velocity of the phonons is low, and that's at the L point. So, okay, L point, what's the L point? 16 terahertz, 16.5 terahertz or so, that's where it is. So the thinking is that in the single laser experiment was found to respond to the compressional, to P polarization, which coupled to compressional plasmon modes. So the idea here is that coupling to compressional modes, the optical phonon modes have higher frequency, and so, you know, in those days I was thinking maybe there's a multi-quantum fractionation effect. And so if the phonon mode energy were higher, you'd need to fractionate less, and that would clearly be the preferred mode that you go to. So, and then if you get the energy there, you want it to stay there. So I said, well, you know, those are the two frequencies because those correspond to the places where the energy doesn't leave if you put it there. So Dennis says, okay. Then of course I forgot about everything. About 5 years later, Dennis emails me and says, Peter, I have some results. And so here's an example of results. These were from experiments done in, say, 2007, 2008. So here there's no excess heat. Actually, I showed this before on Monday. The two lasers turn on, and there's a substantial excess heat event. The absorption from the two lasers is about 15 milliwatts. We're seeing an excess heat event, more than 300 milliwatts here. And there are many examples of this. So Dennis did a very large number of measurements over 2 years. And his system was pretty stable. And he's able to plot the results of measurements at different difference frequencies. So this is excess power, sort of, in these experiments to figure out the excess power. What we do is we take this value, and try to figure out this value. We do that for a very large number of experiments. And from that, we construct what looks like a spectrum. And Dennis says, well, there's these sweet spots. I said, well, it's good that there's sweet spots. Let's see the data and let's plot it out and let's see if we can check it out and see what's going on. So here's one of the sweet spots. It's at 8.5 terahertz or so. Here's another one of the sweet spots. It's just a little bit north of 15 terahertz, so we're 2 for 2. And Dennis also sees something at close to 21 terahertz. Dennis as well. You know, 8 terahertz, 15 plus terahertz, that sort of corresponds to what you're talking about. So tell me, what's a 20 plus terahertz? Well, it's you know, you have to, angels dancing on the head of a pin. You understand how theorists, you know, a good theorist can explain anything. So this is what was seen. Let me talk a little bit about the phonon mode structure. So here, here's the spectrum that we'd actually talked about earlier on Monday when we were explaining that condensed matter had nothing to do with cold fusion whatsoever. So these are acoustical phonon modes. And what acoustical phonon modes is, well, basically they're vibrational waves going into the metal. And these are at relatively low frequency being 6 terahertz and under. Well, it's actually very high frequency in the grand scheme of things, but these are considered acoustical phonons. So here what's going on is that palladium is doing the moving. The hydrogen that's in between is moving along with the palladium primarily. So there's order between the motion of the light interstitials and the heavier metal atoms. The gamma point is the point where there's no modulation of the wave. If you're going in this direction, going in the x direction, then if you remember back for the checkerboard, you're sort of going along one of the planes towards the nearest neighbor. You've got waves that are modulated going in that direction. So these are other directions as well. So here's the gamma point, and around the gamma point, if you put the energy in, it's not leaving. And it's not leaving because there's curvature is, not curvature, the slope is 0 at this point. So this is the compressional mode. The compressional mode happens to have a 0 group velocity at the gamma point. So that was what attracted my attention to it back in first talking to Dennis. And this is the L point, this is the other point, so it's the compressional mode, it's the highest frequency point in the spectrum, and that was going to be the other place that's interesting. So here it's at a little bit more than 16 terahertz, and Dennis's experiments slightly under 16 terahertz, but it's a pretty good match. So we have some understanding then of what this guy is. This is the gamma point, this is the L point, but what the heck is this guy? So there are a number of conjectures as to what it is. Here's one conjecture. And this conjecture says that, well, in your heavy water, you've got a little tiny bit of light water. And if your heavy water ever sat around in I don't know how humid it gets in Austin in the spring, but if it gets at all humid, you can get some light water going into your heavy water. We talked about the solubility. Solubility is like 8 times higher for protons than for deuterons. So if you got 1% contamination of light water in your heavy water, then you're going to have maybe 8% or so in your electrode. So what I did is I said, well, let's try an ordered vibrational calculation, assuming 12% hydrogen in your lattice, and I had to assume order to get a curve like this, but what I find is that the L point for the hydrogen shows up somewhere close to 20 terahertz. And if we go back and look at the data, here's 20 terahertz. This is a little bit higher than 20 terahertz, 21 plus terahertz. Close? I don't know. I mean, it's a conjecture, but it's not been proven. But it would be consistent with the basic picture. So, the 2 laser experiment. Okay, we know that there's no commensurate energetic reaction, so we're interested in where the energy goes. So in the 2 laser experiment, the excess power responds to the beat frequency, and if you think about it, it's almost like we're using the beat frequency drive to produce some vibrations initially in the optical phonon modes. And that seems to be stimulating the reaction. Now, in a laser, if you provide some initial stimulation of an atomic transition inverted system, well, the energy that's produced by atoms de-exciting goes into the same mode that causes the excitation. So coming from a laser background, I looked at this and I said, that kind of smells like it's a laser. Putting in some vibrations, and it seems to be drawing the energy into the vibration. Now, the key issue is, if that's true, the question is what happens after you turn the lasers off. For example, you remember for the 1 laser experiment, it's a switch. You turn the laser on, the excess heat goes on. You turn the laser off, the excess heat goes off. Well, what about this? It said, Dennis, what happens when you turn the lasers off? Dennis says, well, the thing keeps on going. It won't stop. How do I stop it? I said, Dennis, do you have a hammer? No, actually. So the issue is that if the excess power persists after the lasers are turned off, if these ideas are remotely right, if we stimulate optical phonon mode to induce the excess power in the first place, and then when you turn lasers off, if it keeps on going, that sort of suggests that the nuclear energy that's being produced is finding a way into those optical phonon modes. So that's the interpretation. It's a strongly indirect evidence in support of this interpretation. But it is an interpretation, and from my perspective, it's not such an unreasonable interpretation.
How long did the effect persist when you came up with lasers? Do you have any data on that?
In the experiments that were done in 2008, the excess power would persist at the constant level for a couple of weeks when it was driven on the sweet spot. And then after a couple of weeks, Dennis wanted to do something else, so he terminated the experiments. The excess power didn't go away on its own. It persisted, but Dennis terminated the experiment so he could do another measurement. Now, in more recent experiments in work that's going to be published in JCMNS shortly, there's new measurements that have been done where the time history in a more recent experiment is shown. And in that case, at the frequency that was done, we can see the excess power going down slowly after the lasers are turned off. So I think how long it stays on depends on which beat frequency that you use. And from no reduction in over 2 weeks to slow variation over the course of a few days is the kind of thing that was seen.
And was laser in those experiments the only excitation, or did you also have a current further?
Well, there's an electrochemical current.
Okay.
The system starts out being like a normal Fleischman-Pons experiment, but it's just driven a little bit below threshold. So it's close to going, so if you turned up the current, probably it would go. But in this case, instead of turning up the current, put on 2 lasers, and that seems to stimulate the other.
That's a DC current. There's no experience with AC currents tuned to like the super high frequencies or anything like that.
No, Miss Dennis runs with presumably DC current. There's ripple on it, but it's a small ripple. Other comments and questions? This is one of my takeaway message kind of slides. So.
Any of did materials depend on these optical phonon modes, like different material constituents in the palladium cause like the modes to be different, or the frequencies to be different, or maybe last longer, or have more like I don't know interatomic damping to sort of cause these things to not go into these oscillation modes that persist.
Your question's a fantastic question, and it's leading up to some of the big arguments we're going to be dealing with tomorrow. But for now, it is the case that if you have a different metal hydride, then the optical phonon frequencies will be at different locations.
Right.
You can imagine that instead of exciting the optical phonon modes, perhaps if you excited the acoustical phonon modes, maybe you could get the system to run with excitation of acoustical, compressional acoustic phonon modes. And that's going to be really interesting to us first thing tomorrow. Here we see that in Dennis's experiments there was no response whatsoever near 5 or 6 terahertz. There was no excess power seen.
It's interesting that the highest power spike on that is the 20, though it's the highest power on that chart.
Yeah, actually there's another point that on this chart is too high to be plotted. So what happened, it turns out that in this data we were a little bit naive in that the conditions weren't identical for all the experiments. Some of the experiments, for example, this one was running a little bit higher temperature, and we argued the other day that excess power is much higher at higher temperature. So we recently went through and reanalyzed the data, taking the temperature into account, taking the magnetic field into account, and we get the same basic result, but now all the data can be plotted on the same graph, and we get some information about the temperature dependence of the system.
I have a question. Where does this frequency range sit relative to the IR?
Infrared, at least from my perspective, is kind of like over across the hallway.
I wonder if you could decrease the error bars and get better fits. Because in 2003, a number of people reported the application of light to a working cold fusion system, and one of the things we reported was that we got the best results at the top of the optimal operating manifold peak. So to hit it sub-threshold, I wonder if we could improve the data by doing it up on the top.
It would be fun to get the data, to get more data sets of this sort. At the moment, we've got Dennis's result, which took Dennis 2 years of very, very tough work working with the system to get this result. And then we have a more recent set of runs that Dennis has had to come back to revisit some of this. It'd be fun to get a thing done systematically. It would also be fun to get it done systematically for a nickel hydrogen or nickel deuterium system.
Really? And nanors, it go right through.
Yeah.
Yeah.
Why did it take so long for him to do the experiments? Did he have to go through multiple Fleischman-Pons setups to get one that was operating and then run at a threshold, or what took so long?
Well, for example, one of the points might be a weak run, for example.
Typically with aqueous systems, again, if you run between 50 cc's and 100 cc's, which most of the people in the field do, each point there's a couple of days worth of work, even without calibration.
Okay, let me now revisit the issue of deuterium flux. We talked about this on Monday. Mitchell talked about it as well. And I want to come back and think a little bit about it. So in Fleischman-Pons experiment, it was noticed that excess heat seems to improve when you've got deuterium flux present. So for example, this is excess heat from, I think, Kunimatsu. And this is current density. So here's 100 milliamps per square centimeter. Here's 1 amp per square centimeter. So excess heat increases as a function of the electrochemical current density. Now, if the electrochemical current density is bringing deuterium to the surface, this corresponds to a flux of deuterium in from the surface, and deuterium is leaving from Tafel reactions from the surface and from internal surfaces, as we discussed earlier. So if I look at the electrochemical current density as bringing deuterium that's going to flux through the surface, I can interpret this excess heat then as the excess heat responding to flux. And this was seen by many. Here's data from Ed Storms showing a threshold. If you don't have enough current density, you don't get any excess heat. And then once you reach the threshold and go up, you go up linearly. Mitchell didn't talk about it, but you saw the same kind of effect at much lower current density. So in the M4 experiment that we talked about earlier, there was something interesting that happened. So in that experiment, we have an excess heat burst. We have another excess heat burst. And this is the loading. And this is the current density. So there's a current ramp, constant current. So if you look at this and you think about it, according to Mike's point of view at that time, the current ramp is what initiates an excess heat burst. So here's the current ramp. Here's an excess heat burst being initiated. Excess heat comes up, it comes down, and then it turns itself off. Now over here, the current's flat, but another excess heat burst is induced. Also, the loading is highest here, and the loading is a little bit lower here. You kind of think that the excess heat burst ought to respect the higher loading, but it seems to be happy with whatever it is that's going on here. Now, Mike is a seasoned electrochemist, and he's looking at this data, and he's saying, I see something here. I see that the excess heat turns off suddenly here, and if I look at the loading is pretty stable here. Whereas here, the loading is going up and down sort of very fast on the scale. Time of electrolysis, hours, these are a lot of hours. And he's scratching his head, and, you know, electrochemists look at the cathodes almost like they're children, and use these anthropomorphic analogs to understand it. So in this particular case, the cathode is breathing. It's breathing in deuterium, it's breathing out deuterium, and it's doing it on its own. These cathodes have its own personality, so it's breathing, it's breathing, it's breathing. And the breathing is producing excess heat, and when it stops breathing, excess heat just goes down. So Mike looked at that and said, loading is not the only thing that induces excess heat. The flux of current through the surface has got to be connected to the excess heat. So he took, this is a blow-up of the data to show. He put together a model of the following form. He said, well, let's take the excess heat. We know that it goes roughly linear above a threshold. So no current, no excess heat below a threshold current density, and then it goes up linearly. So he put this in. We know that the excess heat goes roughly parabolic above a loading of, say, 0.84, 0.85 or so. And he said, let's add a term that has to do with the flux. Now, theta is the loading in this case. So d by d loading d time, well, if the loading increases, that means deuterium is coming in. If loading decreases, deuterium is coming out. So Mike went ahead and put together a fit like this. This is a fitting constant, so if there's more area, then maybe it's bigger, you get more excess heat. So he took this and he used this model to fit with the data. And here's what happened. So the blue is the measured excess heat values, and the green is what would be predicted giving his fit. So he comes away with the conclusion that, yes, deuterium flux across the surface is important in making excess heat. We talked about the very high excess power result in the energetics experiment, and we talked about the super wave, and remembered about the stuck desk drawer that we're yanking, trying to pull free. Now, if you think about it, this is run in galvanostatic mode, so the current's being controlled. The current's being forced to follow this complicated pattern. This is the electrochemical current. Electrochemical current's high, you bring a lot of deuterium to the surface, the electrochemical current goes back down, some deuterium comes out, make it high, it goes in, it goes out. So this current protocol is one which is going to maximize the flux of deuterium across the surface. In a sense, retrospectively, if flux is really important, it's probably not surprising that a gigantic result was obtained with this very interesting current protocol. The question is, what does the flux do? So if you think about it, how does the deuterium move through the lattice? Well, at very low temperature, it starts in one place and can tunnel through the barrier, goes from the O, perhaps through a T site, then to another O that's unoccupied. So it's kind of like an indirect way. So at low temperature, if it's pure tunneling, there's no vibrations. It's this coherent motion from one place to another place. Now, of course, room temperature is not low temperature. So the picture here is one that's a little bit different. You basically have to have local vibrations to kick the deuteron up from the O site up to the T site, which is 200 milli-electron volt rise in energy, which is actually pretty big. And then once you get there, well, you go down to the next O, but going down is a lot easier than going up, because if you're up there, you got the energy, and if you're going down, then you got all this energy to get rid of. So if you like, the tunneling under thermal conditions is one of getting kicked up, and now you've got the energy, and then when you go down, and now you have all this energy, so you go rattle, 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 and the coupling with other deuterons is reasonably strong. So deuterium flux, through that argument, is would be expected to be extremely efficient in exciting optical phonon vibrations. Basically, this going up and then coming down and banging into the other deuterons to dissipate the energy that you accumulated to get to the T site, that means you're going to be making optical phonon energy. The question is how much energy? Well, it turns out you're associated with this mechanism if you happen to have a gradient in the deuterium concentration and you're driving a diffusion version of the effect, then the power dissipated is going to be the current times the incremental change in chemical potential. So you take the power, you express the current in terms of the Onsager coefficient and chemical potential number of deuterons, and you get a relationship between the power and the deuterium flux. And basically, you can start to get an estimate of how much power. It's not a lot of power. So if you think in the LETS experiment, you're putting in laser power initially into the optical phonon modes. Well, you got 15 milliwatts being absorbed total, but only a small fraction of that's making in the optical phonon modes. Here, you've got some amount of current. You've got power per unit volume. The power here is low. It's small. It's sort of on the same general order as what LETS is putting in to get his optical phonon mode excitation. I'm thinking that the current, this flux business, is providing optical phonon modes, and that's sort of doing the same kind of thing as what's being done in the two laser experiment. So if you like, not only do you have to make vacancies, you have to load, you have to make your molecules, but you have to excite your vibrations in order to get the thing to kick on. So that, in my view, the flux is a very important part of it. Now, Fleischman made a big presentation at ICCF4, and I started talking about the cone effect, and the current effect is one where you basically run an axial current down a loaded wire, and you have more deuterium on one side than on the other, so you can induce higher loading on one side. So Fleischman was interested in using this effect in order to get higher loading. Of course, retrospectively looking back, this kind of effect, if you have a large axial current, you're also moving the deuterium and you're making optical phonons, because a flux is going to be wiggling the deuterons. Now, Celani, back ages ago, before he's famous for the wire, was famous for his results for axial flux experiments. So he put a very high voltage and drove deuterium axial flux one way, electrons go in the other way, and saw excess power this way. Preparata did a large number of experiments, many experiments, the large axial current, saw all kinds of, saw excess heat and saw radiation coming out of it. Godus at Brillouin has given talks about using pulsed axial current to stimulate excess power. And last couple of years, SRI has presented experiments where they've loaded palladium deuteride cathodes, wires, took them into a cryogenic tank, and used an axial flux to stimulate an excess heat event, and saw gains, energy gains of 50%, factor of 2 or so. Anyway, so what this is suggesting is that this axial flux business, which at this point now we're conjecturing makes the optical phonon mode vibrations, which we see from the LETS experiment, has a chance of stimulating excess heat. So the idea is you get your deuterons there, you get everything prepared, you get your vacancies, and you vibrate it. And by vibrating it, it's required, in my view, to cause the energy to go, and the energy goes into the vibrations, according to the interpretation of the LETS experiment. The excess heat remaining on when you turn the lasers off, the nuclear energy is going into there. I mean, we don't know how yet, but from experiment, that sort of seems to be what's going on.
When you say axial flux, do you mean normal to the surface of the material?
If you like, you've got a wire. So to load it, you want to have the flux going in this way. But the axial flux is the flux going this way.
And where is the surface of the palladium?
Well, there's surface around here, and
okay, thank you.
Small surface here, small surface
thank
here. You. So, summary. I feel like I've just said this. 2 laser experiments suggest that excess power is triggered by optical phonon stimulation. We see the excess power is linear in current density above a threshold. So we're thinking if you don't have enough current density, you don't have enough vibrations. You don't have enough vibrations to cause the nuclear energy to go. When you get enough vibrations, then the thing can turn on. The energy goes into the vibrations. We see that excess power responds to deuterium flux caused by cathode breathing, large axial current. And again, the notion here is that you flux, you cause vibrations, the energy could go into those vibrations. So we get to our takeaway message. The takeaway message is all the same. Let me pause to catch my breath and entertain thoughts or comments or questions.
Has any work been done to look at angular momentum and polarization of optical energy to explore the quantum mechanical? And I'm years away from 803 and 804 here, but I just wonder whether looking at what's going on, taking into account linear and angular momentum forms of energy would be helpful in unpacking some of the mystery associated with what where you ended yesterday.
We'll talk a little bit more about that
tomorrow.
Some tomorrow, but some now. Some studies were done. For example, In the case of single laser experiment, NEF Frascati found that if the electric field polarization comes in like this, you drive compressional waves, you can stimulate excess heat. But if you're polarized this way, there's no excess heat whatsoever. In the two laser experiment, I said, Dennis, well, what about polarization? So Dennis did a series of experiments. If he comes in with wrong polarization for both, no excess heat. If he does one under his conditions that's correctly polarized, the other's not, no effect. If he's got two that are polarized correctly, p polarization, then he gets an excess heat effect. He can also, if he does one this way and then switches it, when he switches it, you can see the excess heat turn on and show up. But we will talk a bit more about the selection rules.
So for the phonon, I'm assuming that's the palladium lattice that's moving and the deuterium together, different wavelengths, or are you referring to one or the other?
Your question's the right question. It's an excellent question. So if you've got a long wavelength acoustical phonon mode under a terahertz, in that kind of mode, the palladium's going this way and the deuterium in the middle is sort of going the same way because everything's kind of moving the same. If you're at the top of the acoustical phonon mode band, you get short wavelength motion. The fastest motion, in which case it almost looks like the two palladium at neighboring cells are vibrating into one another, but the deuterium that's close to this one either is not doing very much at all or is moving with the palladium. In the case of optical phonon modes, there's a big mass difference between the deuterium and the palladium. So for example, at the gamma point, a pretty decent picture is a picture where the palladium is just sitting still and the deuterium is doing all the motion. So at the gamma point, the deuterium is going like this, the palladium is sitting still. At the L point, the deuterium is going like this. That's a really good question, and the intuition that goes along with it's very interesting.
Are these all longitudinal modes, or are there transverse?
Well, there are certainly transverse modes. There's two transverse modes, one longitudinal modes, but the excess heat is associated only with the longitudinal modes. Okay, now we've gone about as far as we can avoiding facing any physics issues, but sadly we can't do it anymore. From the experiment, excess energy, no commensurate chemistry, no commensurate energetic nuclear radiation. Got helium-4, we got a Q value near 24 MeV, but no 24 MeV gamma. And we get excess power versus temperature consistent with helium diffusion leaving the site where they made. We've got excess power requiring the cathode to have been loaded above 0.95, consistent with vacancy formation due to inadvertent co-deposition, high current density, high loading. We've got the possibility of molecular deformation in the vacancy. We've got excess power now seemingly being consistent with the formation of the signal bonded dideuterite molecules. And we've got indication of stimulation and energy going into phonon modes. So now, before rolling up our sleeves and trying to grind out a model, what I'd like to do is to figure out what the heck we're trying to do if we're trying to make up a model. If you like, before ever putting together a model, what you want to do is you want to look at every single input from an experiment that you can get your hands on. Otherwise, if you make up a model and your model happens to be inconsistent with your experiment, then the model's probably not going to be right and not going to be very useful. So from my point of view, the biggest theory problem is connected with what the experiment, again, there's experimental data, there's different interpretations possible. My interpretations I presented here are not the only interpretations. There are people that have very different interpretations of the experimental data. But for me, what it's saying to me is that nuclear energy is finding its way into the optical phonon mode vibrations in the LETS experiment. And for me, that's the biggest theory problem. I mean, before can be able to do anything with like the screening or the microscopic nuclear physics or so. The question is how do you get a big MeV nuclear quantum and turn it into lots of small milli-eV vibrational quantum? And if the interpretation that's being put forth of the experiment's right, there's some way to have efficient energy exchange between systems, quantum systems with mismatched characteristic energies. So if you like, that's in my view, is the theory problem standing in front of us. If you want to make a theory for exoseed Fleischman Pons, this is the problem you've got to solve. And until you solve this problem, you're wasting your time trying to put together a model for Cold Fusion. So let me draw a picture. It's the picture. Here's D2, here's helium-4. So very simplistically, here's the D2 energy level. Here's the helium-4 energy level. This is 24 MeV. And over here is my phonon mode. In a phonon mode, the quantum mechanical models for it is like a kid on a swing going back and forth, and the energy levels are quantized, and the energy levels are quantized, say at the gamma point at like 33 millivolts. So the question is you got to, if you're starting from here, you got to go 1, 2, 3, dot, 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 dot. You got to add up lots of 30 millivolts until you make up 24 MeV. And well, it's something in the general neighborhood of 1 billion of them. You scratch your head and say, you know, maybe there's simpler theory problems in other fields. And that's the only rational response. Nevertheless, let's give it a good shot, right? We can take the first steps in this sensibly and rationally. If you come in to a frequency doubling crystal and you've got phase matching working, you can come in at one frequency and you can produce energy at 2 frequencies. So you can change red light into green light. Some of you have probably seen this in physics lab demonstrations and so forth. This kind of notion goes much further. People have done experiments where they come in with a laser that has relatively low energy, but if it's intense, you can have atomic interactions where you convert 1, 2, 3, 4 photons to produce an excitation. So for example, years and years and years ago, data was taken like this, where energy levels in xenon and krypton way up here were accessed and measured using laser wavelength at much lower energy. So in this case, we've got enhanced or multi-photon absorption interaction effects involving 4 quanta. You can find other papers where people have done higher intensity, whack things harder, and seen interactions with more than 10 quanta. Rydberg studies have been done with, for example, 30 plus quanta. This guy here is maybe the granddaddy of this kind of thing. IR laser light goes into gas-filled waveguide, and you get a beam of X-rays coming out. And it's an upconversion effect. It's stunning. It's called high harmonic generation. So for example, collimated X-ray emission seen up to 3 kilovolts. In this particular case, it corresponds to high harmonic generation, 2,500, 3,000 quanta. So what's happening in these experiments, you're starting out with small quanta and you're adding an awful lot of them together to produce a large quanta. And you're doing it coherently, and you're doing it with some non-trivial amount of efficiency. Now, in high harmonic generation, the way that it works is, it's this really bright quantum electrodynamics fellow Corkum that proposed a mechanism. So you start out with your electron in your atom, tunnels through the barrier, it goes out when the field's strong. Now the field's weak, so it just heads on out. Now the field reverses, it comes back in, and when it comes in, it can radially decay. But this happens the same for a lot of atoms, and they're all in phase. So you can end up getting coherent phased array collimated emission going out, and that's the physical basis for how this effect works. So the message here is you actually can combine many quanta to make a big quanta from lots of small quanta. It's done in experiments every day in different laboratories. Another message is that for it to work, you've got to have a mechanism. And in this case, we can see what the mechanism, we can see how it works. Electrons leave, they come back, they gain energy in the process, and then when they radially decay, they're all in phase. That's how it works. So mechanisms understood. Now, the headache we've got right here is that instead of a paltry 3,000 or 10,000 or so, which has been done using Corkum's mechanism, we need 1 billion. And sadly, there's no like super intense laser field that's going to be moving electrons and stuff, so we can't use Corkum's mechanism in palladium deuteride. So the argument is that there are mechanisms which can do this kind of thing. They're known, they're studied. It's not terribly strange. Another issue which is going to become very important for us shortly has to do with phased array collimation. So for example, if you have lots of antennas and they're in phase, you can get directional radiation. Now if you've got atoms, and if they have dipoles, if their dipoles happen to be in phase, you have the possibility of getting phased array emission. So for example, high harmonic generation produces directional beams only because of phased array emission effect. We'll be, like I said, we're going to be very interested in that shortly. Okay, so from the cold fusion experiments, the experimental evidence subject to interpretations and inferences seems to suggest nuclear energy is being converted directly to optical phonons in the LETS experiment. Perhaps in the Fleischman-Pons experiment, if you think you're making optical phonon modes with the flux and the energy is going into the optical phonon modes. Now the giant theoretical headache is the nuclear quantum is MeV and the phonons are milli-eV, and we got a 9-order magnitude conversion. And like I say, any physicist with some sense would look at this line and then go find a different problem to work on, because 9-order magnitude fractionation effect is not the kind of thing that's going to be an easy thing to do. And even if you find it, you're not going to find any of your fellow physicists who are going to believe it. Okay, so coherent energy exchange with massive up and down conversion is certainly known. A few thousand quantum in high harmonic generation. But at this point in the discussion, we're not sure if it's possible, period, to do in connection with cold fusion. And if it's going to happen at all, we're going to need a mechanism to do it. So if you like, we now have our first physics theory homework problem lying in front of us. We need to make a model to take a big quantum and chop it up into a lot of small quantum. Okay, takeaway message time. I get to catch my breath. You guys get to ask questions. Questions or thoughts or comments?
Just thinking about that. Would you like to know if we have a brainstorm of phenomena that this can produce heat? So in a certain way, this is a conversion of.
I actually agree. If you're producing energetic electrons or ions, in the process of slowing down, you're going to make Bremsstrahlung radiation, and that would be a perfectly acceptable way to start from energetic radiation and knock it down into heat. So that's good. Now, the headache with Bremsstrahlung is that if you start with an energetic electron or energetic ion, the Bremsstrahlung is at high enough energy to go out, which means you could detect it directly. You can detect it directly, then you know the energetic particles are there. However, at the moment, there's no evidence that there's Bremsstrahlung in the relevant regime. Moreover, if you started with an electron with multi-MeV energy, many MeV energy created near the surface, it's going to be making it out of the cell. You notice it. So then you think instead of electrons, it's going to be ions. But if it's ions, then you're going to have knock-on DD collisions, which means you're going to get neutrons, and we know that neutrons aren't there. So at the moment, I'm of the opinion that you've not got the fast electrons or the fast ions to make the bremsstrahlung to do the conversion. Other comments? This is a very, very good, very interesting and very good comment. If you like, I would much prefer to deal with the more conventional way of reducing energy. I'd love to start with something energetic and knock it down to lower energy by lots of sequential collision processes. But the experimental data doesn't support that as an explanation, at least from the way I understand it.
Is there any way to sort of, we're sort of assuming that you're going from D2 to helium 4 in one step and you're getting 24 MeV out. Is there any way to kind of break that down?
There are.
To smaller chunks that I know there can be significant.
There are. And the models that we're going to be chewing on here for the next hour or so are actually do exactly that. I mean, by the time that we're done today, we're not going to see it, but that affects actually within the models under discussion. The models do exactly that. Other comments or questions or thoughts? Okay.
Do you think that it is the reason that leads when the excess heat starts, so the nuclear reaction starts, they start not at a single site, but suddenly a high number of sites. So
again, a very shrewd observation. I don't think there's any possibility whatsoever of having a massive fractionation process occur with one atom or one nucleus. There's the models we'll be talking about involve many acting together.
Does this border on your suggestion yesterday, is we may need to confront condensed matter physics, where we're talking about large numbers?
We are going to confront condensed matter physics, and not too terribly long from now. Okay, so I want to talk briefly about the spin boson model. And to preface the discussion, there's no reason that any of you have ever heard of the spin boson model. And the reason that I'm interested in it has actually to do with a lot of history. But back in 1989, when I first got started on this, the question is how do you solve the problem theoretically? And previously I'd worked on X-ray lasers, and for the X-ray lasers, it wasn't clear how to solve that problem. And my boss at that time said, well, what you do is if you don't know how to solve it, put together a model, one that's, select a scheme, even though it's going to be broken, and analyze it. So then you analyze it by going through the process of analysis, you figure out why it doesn't work. Once you figure out why it doesn't work, then you can propose a new scheme which isn't not going to work for that same reason. It'll not work for a different reason. You analyze that, and then in the process of going forward, eventually your models are going to, your schemes are going to get better and better, and you're going to get to it. So in the X-ray laser business, I ended up analyzing 45 different models before I got one that I was happy with, and that process took many years. So here, my same boss so the opinion, well, clearly there's no place to start, so just pick a model, analyze it, and go on. So back in 1989, I picked a model, I analyzed it, I killed it, I figured out why it didn't work, and I proposed another model, I analyzed it, I killed it. And after roughly 100 or so of these exercises of proposing models and killing it right and left, I was starting to accumulate a lot of headstones in the backyard for dead models taken out in the back and buried. And at some point it became clear that instead of analyzing individual models, that I didn't actually have to analyze individual models, that there were certain features of a model that was important. So for example, suppose I had some complicated nuclear system with a ground state and lots of different excited states and different transitions. Well, instead of working with all of the different transitions, all the different states, what I could do is focus on two of them that within the context of the model are most important. And if I did that, then I get, if you like, in quantum mechanics, it's called an equivalent two-level system. So you take an atom or nucleus or molecule, which has got all kinds of moving parts, but if you're only dealing with a couple of levels, pull a couple of levels out, throw away everything else and analyze that. The math is simpler. So what I ended up doing is I got to the point of saying, well, I'm going to have a two-level system stand in for my nuclear, atomic, or molecular levels. And then for the condensed matter part, we can have vibrations, we can have optical phonon modes, we have acoustical phonon modes, we have plasma modes. In a sense, the quantum mechanical description for them is of an oscillator. So the question is, instead of dealing with the phonon mode or plasma mode or this, that, let's just plug in an oscillator. So at some point I got down to just analyzing two-level system, oscillator. So I took my Hamiltonian beat, two-level system, oscillator, plus coupling between them. Now, for those of you who don't know what Hamiltonians are, the best way to think about it is a Hamiltonian is a fantastic way to figure out what's in your model. So you take your Hamiltonian, you get a Hamiltonian for the two-level system, you get a Hamiltonian for the oscillator, you get a Hamiltonian for the coupling between them. Now, at this point, I'm going to ask you to presume that once you've got this, that it's possible to do the analysis to figure out what the model does. So the important thing here now is to figure out what goes into the model. So now we're talking about two-level systems, standing in for the nuclei, an oscillator standing in for the vibrational system, and a coupling between them. And you can have any kind of coupling you want. And of course, the math is simpler if you have a simpler coupling. So what we end up with, turns out I'm not the first one to go through this exercise, of course. This is very famous in quantum mechanics. And one of the models in the quantum mechanics, which is one of the best known models that there is, and there's pretty much more papers on this model than any other simple model in physics. It's called the spin boson model. So this is the Hamiltonian for the two-level system. And this is the Hamiltonian for the oscillator. And this is the Hamiltonian that describes coupling between them. And this is the simplest possible coupling you can have. It says your two-level system can go up or down, make a transition, and in connection with that, you can either make or destroy a phonon, or a quantum, an oscillator quantum. So there you have it. The earliest versions of the models were studied by Bloch and Siegert in connection with my early NMR work. This was adapted when the laser came to describe interaction between light and atoms, and today is used all over the place to describe everything. And if you like, the quantum version of this was popularized by Cohen Tanucci. So that's one of the reasons why there's so many papers. Now, this model does what we need it to do, sort of. If you've got a two-level system that's an odd multiple of an oscillator, so if you have a lot of oscillator quantum making up the two-level system quantum, the spin boson model describes energy transfer between them. So here's results from a direct brute force solution. Here's my two-level systems being described by the associated Dickey number. So I have 100 two-level systems, so this is like 50 plus and 50 minus, and this sort of says all of them are excited, all of them are de-excited, and they go from being excited to de-excited, excited, de-excited. And this is the oscillator, so I have a lot of phonons in the oscillator, and when this de-excites, the number of phonons goes up, or the number of oscillator quanta go up, and then it goes down, go up, go down. The time scale associated with this is quite long. the coupling in this model is reasonably strong, but even though the coupling is reasonably strong, it actually takes a long time to get the energy to go back and forth. And the way it works is you have a lot of individual up and down two-level transitions each time you communicate an oscillator quanta. And if you can maintain coherence long enough to go up and down and up and down enough to give the oscillator enough quanta for it to be happy, then it works and you're in business. So here's an example from the best studied model in physics for interaction between two-level systems and oscillator, and it's showing a version of exactly the effect that we would need to happen in order to make this stuff work. Now, sadly, this is only 17 quanta. We need 1 billion quanta. So, like I say, baby steps, maybe. So how does it work? It works through coherent sequential exchange of one quanta at a time. You exchange it over and over again while maintaining coherence, and that picture agrees with analytic and numerical calculations. So takeaway message. So I want to describe fractionation of a very large quantum. The fractionation of an MeV going to millivolt is not something known in the literature. The spin boson model, one of the best understood models in physics, describes a weak version of what we need. So, okay, takeaway message now. Comments, thoughts, questions? Okay, how many of you are willing to bet that we're going to be able to hammer on the spin boson model and get it to do billions rather than the 17?
Do it over and over again.
Okay, so the question is, why can't we fractionate a large quantum? I mean, we can fractionate a sort of large quantum. We can do 17. Why can't we do 1 billion? So, issue is, okay, we know spin boson model does a weak version of what we need to do. The question is what limits the spin boson model? So spin boson model can exchange energy between mismatched systems where there's a modest amount of fractionation. But we need coherent energy exchange with a large amount of fractionation. We need something really big, chop it up into a gazillion. And so the question is why in the world does the spin boson model run out of steam? Because if we can figure that out, then maybe we could fix it and get a new model that doesn't run out of steam. Now, one way to ask the question is to go into perturbation theory. And perturbation theory, the coupling's weak. What you do is you can write down, you start at one state, you have all the states that you connect to, and then once you get from here to here, you can go from here to either here or here. From here, you can go to here or here. And if we want to go from here and end up here, in essence, to fractionate a quantum, you want to start at one state and go to a distant state where there's no direct coupling, but you've got to go through all these intermediate states. Now, the cool thing about perturbation theory is sort of simple, where you can set the thing up and you can calculate everything out and you can get an answer. So in this case, you can calculate the contribution from all the different pathways, this way, this way, this way, this way, and you can add them up. Now, contribution from each pathway individually is actually pretty big, but all the ones that go this way contribute with one sign, and the ones that go this way contribute with the other sign, and there's sort of as many up here as there are down here, and it's sort of almost sort of symmetric. And so by the time you end up adding everybody up, they cancel out, and they cancel out. I mean, it's sort of like each of these terms are like having $1 million bill, and you add them all up, and by the time you're done, you've got half a penny left or something. I mean, the cancellation is so efficient that the contribution of one pathway for this simple problem, the sum of all the pathways is less than 1 part in a million, the contribution from any single pathway. So the basic conclusion is the reason the spin boson model can't do it is due to destructive interference among the different pathways. So you can argue this for 3 or 5 or 7. You can go through it. And, you come to the same conclusion every single time. So that's the problem. I could just fix that, and then I'm good. So the issue is we've diagnosed the system. We know why it doesn't work. Now the question is, can we fix it? Can we make a version of the model that does work? So I tried, instead of linear coupling, I tried nonlinear coupling. I tried a nonlinear oscillator. I tried more than one set of two-level systems. I tried more than one oscillator. I tried the kitchen sink. Put in the kitchen sink and model the kitchen. It didn't work either. Nothing works. Destructive interference is very robust.
Just an idea. There is a similar, maybe similar problem on the fluid dynamic regime. In particular, when you need to dissipate energy at high Reynolds values of flows. So in that respect, there is no dissipation at high Reynolds. So Kolmogorov made a model that is the cascade of energy. In that way, you transform the energy from large eddies to smaller and smaller energies till they go to the small eddies where
Right.
dissipation can occur.
Right. Well, if you like, the cool thing about the spin boson system is that when it does work, it works coherently. It's quantum coherent. So the normal breakdown of energy would be incoherent. And one of the issues in all this is I was kind of hoping to get a coherent model that was capable of fractionation. There's technical issues, but when it comes to modeling cold fusion, it makes like 50 orders of magnitude difference. So I kind of like have my heart set on having a coherent model that can do the job. So you analyze model after model after model. These were sort of models between 130 and 150. So they, shot them, buried them out in the backyard, and continued on. So by 2002, an unbroken string of dead models, becoming more and more efficient at killing models off one after another. Unbroken string of failures, 12 and a half years of effort. Somebody smarter than me would have found a different field by this point. My wife says that I'm stubborn, but I assure you I'm not stubborn. No matter what anybody says, I'm not stubborn. Okay, so the takeaway message. We want to fractionate a large quantum. We now know, we understand why the spin boson model runs out of steam. Many tries at hammering on the spin boson model to change it in some way to make it work better. And the result of the effort is failure, failure. See, unbroken string of failures here. And I actually came to the conclusion that it was impossible. I concluded that there was no way that you could do it. So in fact, at that point, I got to the point of saying, let's put together a mathematical proof now that it's impossible to fractionate a large quantum. I had enough evidence, I had a model, well-formed question. I could now specify this as a mathematical problem, and I could come up with a proof I could construct as to exactly why this couldn't work, which the implication would be is that, of course, the experimental results have to be wrong. Experimentalists are deluded, so forth and so forth. So this is the direction it's going. So it's my takeaway message. Time for me to take a breath. Comments, questions? No comments, no.
Are large gammas ever seen, ever?
Not 24 MeV gammas.
Okay.
There is some gamma emission, but we'll talk about it. But it's at very, very low level. And it will help us learn about the system.
What would we do to instigate the release of large gammas? Are there anything that we know that we can do to Try to break the safety of the system. The safety of the system.
You're getting ahead of my story.
Okay.
But at this point, I suppose the thing to do is to say, thank you for your attention. Very possible. Mitch.
Large gammas are spin forbidden anyway, though, aren't they? I mean, when you look at hot fusion, you see a 50% branching ratio for the
It's not a question of spin forbidden. It's
Okay.
a question that the nuclear interaction is much stronger than the electromagnetic interaction. So processes that are mediated by the strong force just happen much faster. And the electromagnetic thinking slow.
What about the theory of fractionate the emitted radiation energy, like split up the gamma into like say it doesn't emit just one gamma, it emits 10, 4 MeV somehow.
Of those headstones that I was illustrating, some of the headstones was analyzing exactly that
Right.
problem. I set up models to say, well, instead of 1 gamma, how about 2 gammas? Let's work that out. And then let's do 4. And I worked that out, and then not very far after that, I found that things were going south exponentially, and that it was just never, ever, ever going to get to a gazillion gammas.
I have one question. Let's suppose that you do get a gamma, it's a hypothetical case. How would it, if it came out, how would it get dissipated? How would that energy
Depends on
get
the energy of the gamma. The gamma's a 24 MeV gamma. It's just going to go out.
And it's just going to keep going?
Yeah. Oh, it'll go until it finds somebody or some object or whatever. It goes through air long enough to interact. Okay, brainstorm. Let's go back to this perturbation theory business. I mean, if the battle's going to be won, it's got to be won with a simple picture. So the issue is that you go up this way, you go down this way, everybody's contributing and canceling out. What you need to do is you need to make some of these guys look different than some of these guys. So the thought is if I introduce loss into the system, then loss is going to figure out whether you're here or you're here. So here's the argument. The system's got this much energy, but it accesses basis states that are up here. Now these basis state energy is more energy than you've actually got in your system. So that means that, imagine that you've got some decay process where you lose some energy and you'd like to end up here. Well, if you've not got enough energy to be there in the first place, you're certainly not going to have that be a final state for a decay process. So the decay rate associated with states that are up here in this kind of model is actually really, really slow. Alternatively, if you got a state down here, well, this basis state has a lot less energy than what you got, which means that it can actually be a perfectly fine final state for some loss process. Namely, the distance between here and here is quite a bit of energy. So if you've got some process, if the lattice is vibrating and it happens to have some trivial interaction, it's actually got this much energy available to dissipate with this guy as being a potential final state of the system. So in the presence of this kind of loss, if the loss is fast, especially if the loss is fast, these guys are going to, well, if the loss is slow, these guys get occupied by coupling between the different states. But if the loss happens to be faster than the coupling, then you try to couple down here. The loss is really fast. These guys aren't going to have any population. If they don't have any population, they're not going to contribute in the pathway to the destructive interference part. That was the brainstorm, 2002. So, tried it out. And the way to try it out is to start with the spin boson model and add loss. This is called Brouillon-Wigner formalism and so forth, but it's a way to model loss approximately simply in a quantum system. So I said, let's try this out. It's described in a paper 2011, but it was found in 2002 and was presented in 2002 initially. It just took a while to come to the conclusion that we ought to try to write it up systematically and get it out there. So I'm going to think about the new model. So loss can to eliminate the destructive interference. The resulting model, from the very first, we found had dramatic powers of fractionation. We could exchange energy between mismatched system and this model, do it very efficiently, even if we had to have a lot of quantum making up, a lot of small quantum making up the big one. So very good results just from the very get-go. The initial results were computer simulations, and it showed very robust, strong version of the effect. Perturbation theory followed, shows the effect. We analyzed it in the weak coupling regime, medium coupling regime, strong coupling regime. Analytic results work, numerical results work, and we derived a number of approximation methods now to extract analytic results by approximating things, and they agree with the numerical, agree with the analytic, and it works. So, some success. Only took 12 years and 150 models, but we got some success. I'm going to talk a little bit about the result. If you analyze these things, there's something called Ehrenfest theorem. What's really cool about Ehrenfest theorem is Ehrenfest theorem allows you to take a quantum problem, extract the classical dynamics associated with it. So for these models, we can actually use Ehrenfest theorem to get the classical dynamics out of it. And what we find is that it's a nonlinear oscillator. And if we calculate the oscillator frequency, there's basically three parts to it. One part is this, which probably doesn't look familiar, but in these models, this is how it would work if you were on resonance. So if the oscillator and the two-level system were matched in energy, you would get an oscillation frequency, something like that. Now, there's a price if you want to fractionate a large quantum. So this is in the limit where you're fractionating a big quantum into a very large number of small quantum. So you pay an algebraic factor, 1 over the number of quanta squared. And if you look at that, that turns out not to be a particularly strong dilution of the rate. The other factor is this guy right here. And this guy's a hindrance factor. And it basically says, unless you've got enough two-level systems, unless the coupling's strong enough, unless the loss is proper, unless everything's right, then it doesn't work. So this is a hindrance factor. And you can calculate it and plot it out, but it basically says if the relevant coupling parameter is not strong enough, then you're down by a gazillion orders of magnitude and you don't see anything. It just doesn't work at all. But if the coupling's strong enough, then it turns on. And it turns on, and then things can work and it can go. So that's sort of how this model works. So takeaway message. So I have a brainstorm. Eliminate destructive interference using loss. Have a new model that does the job. And the new model describes coherent energy exchange under conditions of fractionation. We have different methods of analysis, and we've tried many, many versions of these models now, and they show the efficient energy exchange effect. So the takeaway message is we now have an important toy model that demonstrates the mechanism that we need to do, what we need to do to understand the excess heat and other anomalies. So this is takeaway message time for me to catch my breath. Questions?
Could you say a little bit more about what you mean by strong coupling? The Ehrenfeld test requires the strong coupling in the case of your work. What do you mean by strong coupling?
There's a parameter here that mathematically describes exactly what the strong enough coupling is. And a way to think about it is that there needs to be some finite amount of coupling there to begin with, but you make the coupling stronger if you have more two-level systems participating. So a small system's not going to do it, a bigger system's going to have better luck. If delta n's too big, then it's not going to work, but if delta n is smaller, if you don't have to fractionate as much, it's easier to get the coupling strong. So going to higher frequency makes it work better. Low frequency, it's hard. Small systems, hard to get it to work. Bigger system, it works better. Having the underlying individual quantum coupling, if it's too weak, it's not going to work. If it's strong enough, then it can work. So we got formulas that we can use now to evaluate anything that we like for this kind of model.
Thank you.
Other questions or comments with that? Okay. So that was 2002. And years afterwards, we've had a lot of years to think about the new model. So the new toy model can fraction enlarge quantum. It's exactly what we need, in my view, to begin making theoretical progress on Fleischman Pons. Now, this toy model says that there's a mechanism to break up a large quantum or build up a large quantum. But on the other hand, this is not something that is normally understood in physics. You can't go to the library, pull down physics papers of people studying mathematical models like this other than my papers. And you can't find anybody doing experiments which seem to show the effect, but they study the effect and see how much fractionation you can do. So the question is, if the effect is real, can it be demonstrated? And this question is going to lead us to some experiments. So I'm thinking about a demonstration. So I went to a conference once and I was presenting my models for how cold fusion works. And one of my colleagues, Akito Takahashi, raises his hand. He says, he didn't like my model. He says, your mathematical solutions, they show that the energy from the D2 going to helium-4 can go in the oscillator, but if you follow your solutions, the energy goes back the other way. That's impossible. I'm thinking to myself, well, coherent models work that way. That's what they do. So the math was going to say that any coherent model is going to work that way. And I thought, Akito, thank you. You've given me the key. If I want to convince anybody that there's anything to this, I need to start out with vibrational energy and go the other way. So what we'd like to do now is we want to start out and put vibrational energy into a phonon mode and see if we can cause a nucleus to be excited. Because if you can go the other way, that will clarify that you should be able to go the first way in the first place. So for excess heat Fleischman Pons, energy is going from the large two-level system transition energy being fractionated down to go to the small characteristic quantum oscillator. But we ought to be able to go the other way from vibrations to nuclear excitation. And so that's now what's on the table. So this is as a way to try to clarify how things work and to figure out if they can work. So the place we're going to start is to say, let's go through a design exercise. Suppose I want to give vibrational energy to a nucleus. Which nucleus should I choose? Well, given that it's hard to do, let me choose the nucleus that has the lowest excitation from the ground state. And I kind of have to start from a ground state because the math says if I start from an excited state, I got no population, so I got no coupling, no strong coupling. I'm going to need to fractionate the quantum. So there's a transition at 1565 electron volts. And so that's going to be the initial focus of my attention. Turns out I'm going to end up getting beaten over the head for this shortly, but that's where I'm starting. So I said, well, look, here's the setup conceptually. Start with a system that's going to vibrate a sample that has mercury in it. And then if mercury gets excited to the 1565 eV state through whatever coupling physics is in agreement with the toy model, then the phases should be coherent, and I ought to get collimated emission. I should get directional emission. So this was the proposal as a design to focus on. So I said, well, if I got my toy model, let me go ahead and put some physics into it, get the mechanism of my toy model to work in the real world, demonstrate this emission, and this will clarify if this mechanism can work. So that's what's on the table. So we calculate away. So I design, I calculate. And to minimize the fractionation, I want to maximize the vibrational frequency, so I think, let's use terahertz vibrations. Calculation says it can be done, but I'm going to need like square meters of surface area to see this. So at this point, it's one of these things which is a Gedanken experiment, but it would be like a mess to actually try to build in the real world. Also, the model said that the emission should be broad, that this thing actually works, and it should be collimated. Now, at some point, it occurred to me that I'd seen a presentation of collimated radiation near 1.5 keV, and that was in the Carboot experiment. So Carboot had this glow discharge, and so the cathode's here, the anode's here, there's like 10 torr of gas, and the effect works with different gases. But he turns the discharge on, he gets some collimated emission. He turns the discharge off, he gets spikes of much sharper collimated emission. And so I'm thinking to myself, aha, you know, maybe what's happened is that what I was trying to design, my design's like a failure, but maybe Carboot's experiment is an embodiment of what I was trying to design. The only thing is his works, and maybe there's something wrong with my models. So that is what's on the table. So here's, the X-rays are very bright. So if Carboot makes a pinhole camera looking down at the cathode, here's the cathode, and here's the radiations coming sort of like from these Bessel function shaped kind of things originating from the cathode going up. And the shape of this suggested, well, maybe there's vibrational amplitude in this round cathode that's anchored around it. So here's what the diffuse spectra looks like. So in this case, he's got a bent crystal spectrometer. The radiation comes up. It goes and it's imaged by film. So here's 1.5 keV. So we've got broad emission somewhere near 1.5 keV, which sort of seemed to be just exactly like what the model was talking about. So here's the spectrum. It's sort of peaked around 1.5 keV. It's broad.
So, Peter, what was the base of the experiment? Is this a glow discharge or something like that?
Yeah. It's a high current density glow discharge. And we were familiar with this discharge because we hosted this discharge on the second floor of Building 38 at MIT. I got to spend like 3 or 4 years working with Louis Smolin on this thing. It's a beast. Back in the early 90s, before he did this, I went to the Luch Institute and visited his laboratory and spent a fair amount of time talking to him. We were trying to measure, there was a claim at that time that they were seeing gamma emission. And we tried to see the same gamma emission. We actually saw the gamma emission that he saw. The only thing is that we understood it to be just noise and rolling the dice statistics and not real gamma emission.
Yeah, but I was going to say that it looks like could it not be a Bremsstrahlung spectrum if you're getting, what would that be?
If you like, some of his spectra, some of his emissions occur a millisecond after the discharge is turned off. So
Yeah.
that emission cannot possibly be Bremsstrahlung. In addition, when the electrons are going towards the anode, the ions are going towards the cathode. So you might say, well, the electron's going this way, could give some Bremsstrahlung. In fact, people have studied emission from accelerated electrons in the discharges, and it doesn't look anything at all like Carboot spectra.
What was the frequency of the vibrational energy put into this system?
In Carboot's experiment, we don't know what the vibrational energy is because there's no direct measurements of it. I'm of the opinion in Carboot's experiment that it's the fundamental compressional mode, which, if I look at his cathode thicknesses, I think is between 100 megahertz and 250 megahertz in his experiment.
Thank you.
There's Carboot, and that's me back when I had hair. There was an earlier experiment which, in light of all this discussion, is of interest and should be mentioned. Gotzi, who we've heard from earlier in connection with time-resolved helium measurements, in his torus of cells, had one cell that produced excess heat, but which also produced close to 10 megajoules of excess heat, but observed roughly 12 joules of gamma energy. Now, what's interesting is that this gamma energy was directional. It gave splotches. And the energy was estimated to be 89 keV, being due to a transition to a metastable state in silver. There's only silver either being a contaminant or being created in the experiment. It was not clear from the experimental result. But I'm actually of the opinion that what it is that happened in Carboot's experiment is actually very similar to what happened in Gotzi's experiment. The collimation requires dipoles phase. Either you require an population inversion to have a laser effect, or you need phase coherence among the emitting dipoles. To get collimated emission, you need phase coherence. In Carboot's experiment, I think you need phase coherence. Carboot thinks he's making X-ray laser. I don't think he's making X-ray laser. So I think this is a separate example of the same underlying effect, but at much higher energy. So thinking about Carboot's X-rays, so conjecture that Carboot's X-rays is due to upconversion of vibrational energy to nuclear excitation. The collimation is proposed to be due to phase coherence. And the phase coherence would be established by the upconversion process. And we have an earlier observation of this kind of effect from Gotzi. Let me pause and catch my breath. Questions? Comments? Thoughts? No questions, no comments. Okay. Kornilova and Vysotsky. Vysotsky showed up at ICCF 18 and he had a poster with X-rays that were at 1.5 kilovolts. I was wandering by and I looked at it and I thought, wait. So I went there and spent the next 45 minutes talking to him about it, came back and talked to him for an hour and a half the next day. I think he's got some results that are really interesting and really relevant to it. The place where it starts is with an experiment that's called the Yang, called the Massoff experiment. For those of you who actually saw this beast when it was in our office, we were working on doing experiments to confirm. The claim was that you put in 800 watts and it produced 5 kilowatts of excess power. It was going to be an early home unit for making excess heat with cold fusion. So we had it in our laboratory. We did tests on it, and after we were done, it went up to the home company to a company in Vancouver, Canada, for testing. And when they were done with it, it went to Kornilova and Vysotsky's lab at Moscow State University. So we are familiar with this beast. Here's the so what you have is you've got like 50 atmospheres of oil pressure, and the oil goes through a little tiny nozzle. This is like hard plexiglass. It goes through and it's squirting out. You get bubbles and cavitation here. We saw the bubbles and cavitation. Now, of course, when I saw it when it was working, there was electrons, discharges, and all kinds of other things happening as well. We never saw that in subsequent things which appeared not to work. Now, what Kornilova and Vysotsky did that we didn't is they brought an X-ray detector up next to this hard plexiglass, and they saw X-ray emission. And they saw X-ray emission which depended on the pressure, but it was run at low pressure, lower X-rays, crank the pressure up, the X-rays move to slightly higher energy. Crank the pressure up, the X-rays move to slightly higher energy. And this thing looks sort of like a car boot spectrum. Now, in car boot's own measurements, depending on how hard he drove it and what material is there, the spectrum, the center of the spectrum would move as well. So it's apparent in his spectra, it's apparent in his earlier measurements, TLD measurements, salinity measurements, and foil measurements. Now, they were intrigued by this at Moscow State, so they worked with a water jet used for cutting metal. And they brought their X-ray detector and they looked at their jet. They also took the detector and looked at the nozzle to see if there were X-rays coming off with the nozzle. And they also did experiments where they put stuff on the nozzle to see if that would make a difference. And what they found was that the water jet would give a spectrum. Here's the spectrum. It sort of looks like what we saw before. And the energy would change depending on the pressure of the water. From the nozzle, they've got a little bit higher energy spectrum. And in some experiments, they put some lead, I think, on the nozzle, but I got to go back and double check. And in this case, they got even more energetic spectrum. An experiment which I think is a really important experiment. I mean, in light of this discussion, I think this is one of the more important experiments that's out there. So what we have is we've got the water jet here. We've got some air, and then we've got a steel plate. So according to Vysotsky at ICCF 18, it's a 3 millimeter thick steel plate. Now, if the steel plate is bare, apparently a very large flux of collimated X-rays come off with spectra sort of like the spectra that we saw. What Vysotsky and Kornilova did is they put paint on the surface of the steel plate. And the paint basically absorbs the X-rays. The X-rays are relatively soft and it doesn't take too much paint to absorb them. But the paint has holes in it. And so the X-rays go through the holes. Here they have 2 pieces of X-ray film in an envelope. So the X-rays go through air, go through the envelope, they go through the holes in the paint, and they give you this pattern. Now, one piece of film's behind the other piece of film, and the pattern in the other piece of film is the same as in the first piece of film, and the pattern also appears to correspond to the whole pattern of the holes in the paint. What this is telling us is that the X-rays are coming out, but they're coming out collimated. It's not a wide dispersal. That in Kornilova and Vysotsky's experiment, we've got collimated X-ray emission, very similar to car boots. So I'm of the opinion that the effect that they're seeing is similar to Vysotsky's car boots effect. Now, Vysotsky attributes collimated X-ray emission to be a conventional effect, which is a result of shock wave formation. I don't actually believe that there's any way to get a shock wave from the water jet through air to the steel plate. I think that the water jet is a wideband, high-intensity acoustic wave noise source, and the piece of steel is an acoustic filter. I actually did some estimates for what frequency you would need to get the emission to be done. I actually think the fundamental vibration near a megahertz is what you have to excite in order to get this to occur. But again, this is not, there's not agreement on this yet. So I'm drawing attention to this for collimated X-ray production, similar to carbon.
In that experiment in the last slide, the direction of that water flow is supposed in and out of the screen right there.
Yeah.
That's
Other comments? takeaway message. So by now there are a number of examples of collimated X-ray emission. Can argue for acoustic excitation, excitation acoustic vibrations in Carboot's experiment. I'm going to argue that this similar high amplitude acoustic vibrations, high amplitude, not so high amplitude, so significant amplitude acoustic vibrations are present in Kornilov and Vysotsky's experiment. They put some effort into measuring their acoustic vibrations. So from my point of view, they were looking at tens of kilohertz regime, which I think is too low to be relevant here, but that's to be sorted out and determined. Kornilov and Vysotsky also saw that their X-rays, the collimated X-rays that produced it, they would bend a plate that was producing them, would cause a focusing of the X-rays, which is, I feel like it's even more interesting because you're getting some phase variation that will cause focusing in your vibrations. When you're up converting to X-rays, and the phase information that's really the focusing is being communicated to the X-rays, so the X-rays are being focused as well. Again, I think these experimental results are absolutely stunning. I think they're far more, they're incredibly important, and at this point they're obscure. Comments or questions or thoughts?
I would agree. This is pretty amazing. So is there any other evidence of any sort of vibration converting into X-rays beyond these reports?
There is.
Okay.
And
can you expand on that?
Yeah, I'm going to expand and say that we have a draft of a paper that we're going to be submitting shortly, which I think provides an awful lot of clarification of exactly what's going on and how this works. I wanted to talk about it and present it because it would knock your socks off, but in deference to my colleagues and so forth, we really need to get our paper out. Okay, back to modeling. So now, we've got experimental data, we've got our toy model. The toy model demonstrates upconversion mechanism. We went through our design examples, but our design examples, as we now know, fall far short of experiment. The coupling mechanisms used for the design models just were far too weak to have anything to do with Carboot's X-rays or Kornilov and Vysotsky's. So at issues, we need a new coupling mechanism. We need a stronger coupling mechanism. So I'm seeking a new coupling mechanism. So I started out, my design was actually based on electron-nuclear coupling. So you get vibrations, the electrons' wave functions change slightly. The change in them can interact with the nuclear through dipole-dipole interaction. So that gives you a way to get some coupling. That's very weak. I also tried electron-electron coupling. You promote an inner shell electron. That coupling is much stronger because the electron wave functions are much bigger. Still too weak by orders of magnitude. The only coupling that was consistent with the models that could have anything to do with these experiments is internal nuclear-nuclear coupling with phonon exchange. The headache is that you can show, and it's something in the textbooks, that there's no coupling between the internal nuclear dynamics and the center of mass degree of freedom. Certainly in the non-relativistic problems, it's clean separation. For the relativistic problem, it's not quite as clean. Anyway, so we tried these models, and they didn't work, so we took them out to the back and we buried them along with the other models. So far, we're running out of room for the dead models. Okay, so the problem's tough. If it's upconversion, then I'm expecting the toy model mechanism, the toy model to apply. The only way to connect with experiment, in my view, is if there's exchange between vibrational quanta and internal nuclear degrees of freedom, because that's the only thing out there that conceivably numerically could be strong enough to do the job. In the non-relativistic problem, there's a clean separation. The relativistic problem starts out having a coupling exactly as big on the order of what you need to do everything. But unfortunately, in a relativistic problem, the strong couplings, strong first-order couplings, usually rotated out, leaving a weak residual coupling. So in the relativistic problem, there's no coupling left that could do the job. But on the other hand, the relativistic problem starts out having exactly what we need. And that's like, it's almost like, there it is. You can see it, you can touch it, you can feel it, you can grab it. There's this blasted rotation that says you can't have it. Very sad. No place to go. So collimated X-rays look real enough. Toy model can account for the up conversion. The only possible way forward is if we can make use of the strong relativistic coupling. But it gets rotated out. In my view, there are no other possibilities. And there's a unitary transform, which is just a basis change, which is known to eliminate the strong first-order coupling. So as a result, once again, we come up against a brick wall for the theory. There's no way forward. There's no coupling. There's no resolution. So I guess what we should do is conclude that the effect isn't real, that Vysotsky and Kornilova aren't measuring what they think they're measuring, the card boot's a clown, and the effect doesn't exist. And the theory triumphs once again over experiment. You don't like that. Brainstorm. Okay, so the brainstorm, if you like, you know, we're in a place where we need the internal nuclear coupling, but the unitary transformation rotates it out. So the thought is, suppose that this unitary transformation breaks. Maybe it doesn't work, but I mentioned this idea to one of my collaborators. My collaborator says, unitary transformation is just a basis change, so mathematically it can't break. I mean, you can always change basis. There's nothing to prevent you from changing basis. But the thought is that maybe, instead of it breaking, maybe it's unhelpful. And it turns out there's an example of where this works. In the lossy spin boson model, you can do a unitary transformation which removes the first-order coupling, the strong first-order coupling. The only thing is that if the loss is present when the unitary transformation rotates the loss, you get a mess, which means you can't do anything with the problem. So in the lossy spin boson problem, we have an example now where the unitary transformation works, but you're not going to use it when you do your analysis, because the problem you get when you don't do unitary transformation is a big mess. It doesn't help. So this gives one hope that maybe we can make progress. So the idea is that you got a Hamiltonian with a part that can be rotated and you got loss. You do your unitary transformation. The part that can get rotated gets rotated, but the loss gets rotated too. And if this is a big mess, then unitary transformation is unhelpful. So this is the brainstorm. Only took an extra decade to get to that brainstorm. This is about 2 years ago. So this now leads us to, actually, if you like it, it leads us back to the standard model, essentially. The idea is now that what we'd like to do is we'd like to use the best physics that we can. We'd like to use the standard model QCD. And QCD has this issue. Normally we rotate out the strong coupling. But if there's loss in the problem, that's not going to work. So what we'd like to do is we'd like to use QCD directly, but QCD is sort of too hard to work with right now. We need something simpler. So what we're going to do is we're going to say, formally we're going to work with QCD basis states in the rest frame. But if things move, we're going to account the movement, even if it's slow move, because the lattice, the velocities are slow. So the idea is that we're going to make a finite basis approximation. We're going to get MC squared, which is the energies of the basis states in the rest frame. So all the different basis states in the rest frame we're going to include here. Now, if the nucleus moves, then there's this Lorentz contraction that occurs. There's all this relativistic stuff that occurs. So internally things change around. But you can describe that in terms of the rest frame basis, in terms of this kind of coupling. So there's the coupling. And normally, this is a very strong first order coupling. Normally you rotate it out. But if your rotation is prevented from working, you got to work with this. So this gives us a model. And here's our model. So we're facing condensed matter physics. What we're going to do is we're going to replace what's in the textbook with a better description. And the better description says when you work with rest frame, finite basis states in the rest frame, energies coupling due to center of mass momentum. So electrons, electron-nuclear interaction, we've got a new fundamental Hamiltonian. Only thing is this fundamental Hamiltonian talks now about direct interaction between vibrations and internal nuclear transitions. We can make a Born-Oppenheimer approximation and we can reduce it to this. So this is energy. It's basically relativistic kinetic energy and related effects, nuclear-nuclear interactions. And now that we've gotten rid of the electrons, there's coupling between the vibrations and the electrons, which is going to give you some loss. So we have loss that we have to include. And there we've got a model. So we now have a model that can...
What's CMNS?
Condensed matter nuclear science. It's sort of what I consider the field. Let me think about the new model. Relativistic generalization of condensed matter physics. If you like, I'm not actually talking about new physics. I'm talking about saying let's do condensed matter, but let's use a better starting place. Let's not remove the first order coupling between the vibrational degrees of freedom and the internal nuclear degrees of freedom, because the rotation that's needed to do that, if you have loss present, has a potential of not working. So we've actually got to do our physics the old-fashioned way. We've got to do it like including what's the physics that's there in the model. And the coupling is sufficiently strong to account for the Carboot experiment. I think what I'm going to do, I'm out of time. I'm going to fast forward. And then I'll come back at the beginning of next time. Basically, after many tries and false starts, now have a demonstration that this model does inverse fractionation quantitatively consistent with the Carboot experiment. There are many issues. One issue is that we now know, as of Tuesday morning, that the mercury F1565 EV transition is not involved. So we have a model now, which the Hamiltonian that I showed you, if you analyze it correctly and you dot your I's and you cross your T's, you can show that it's capable of fractionating, doing inverse fractionation, build vibrational energy up to get you the quanta that observed in the experiment. So I've gone over it, but I'm going to stop here and we'll pick up from this point next time, and we'll keep on going. So let's take our few-minute break here, and we'll reconvene before 10.
I'm going to just briefly review what we've done the first couple of days here, 3 days here, talking about introductory cold fusion. We talked about why we like cold fusion, because the fuel is abundant, because it's relatively safe, we're not making anything radioactive, and apparently there's no penetrating ionizing radiation coming out. And the energy density is off the map, so that's why we do it. Then we talked about the materials that are needed. We like palladium because it has a high carrying capacity from loading, but it's a complicated issue. We talked about the fact that although palladium has a very high diffusivity of hydrogen through it, if you end up cracking it, you get even more diffusion through it, but it becomes non-selective. And unlike some of the people who claim that cracks are the site of cold fusion. We find experimentally that it isn't. And then we talked about briefly the fact that palladium doesn't necessarily have the best permeability, but it has the lack of hydrogen embrittlement and changes that even maybe nickel does. And we talked about the response of these materials to applied electric field intensity. We talked about the fact that most people in the field use very low impedance solution. I'm back in aqueous systems. We're not talking about nanomaterials, excuse me. But that when we get successful results, we try to work with ultra-pure light water and ultra-pure ordinary water and ultra-pure heavy water. Then we talked about the fact that in looking in the AC region, we have a complex permittivity issue. We briefly talked about water. And the way that water works is we generate a cathode fall. It's not that the material changes in the direction of the electric field. It's a diffusion of deuterons in a drift ellipsoid. And what happens is this drift ellipsoid comes down to the cathode and then loads into the cathode. The other thing, by the way, is that in order to get the drift, you have to have an asymmetric infrared vibration or molecular rotation. And that's one of the reasons why, in addition to photoirradiation of the cathode, causing physical effects like Peter described, I think there's also secondary effects in front of the cathode in the solution. Okay, then we talked about the methods of validation and calibration, how we do it. It's easy to measure temperature, but you have to compare it to a control. You want to compare it to non-cold fusion things. We do generate high temperatures with cold fusion, but the trick is two things. One, we want to compare it to an OMA control, and I showed you a number of results where for the same input power, we get a higher temperature with cold fusion, as opposed to the control where we get a lower temperature. The other thing I tried to show you was that it's even more important to switch to thermal power spectroscopy, where we're measuring in power in watts and energy in joules, rather than looking at just temperature, because temperature doesn't tell us how much heat is there. Okay, so in order to calculate it, you use specific heat, you use thermal conductivity. We went through some of that, and we talked about the fact that we like to set up very well-designed geometrically measurement systems where we put the nanors or the fusors next to a control. We put a big thermal mass around it. We make this relatively adiabatic, and we get a secondary measurement by measuring the heat out. So we have two corroboratory ways, if we have excess heat, of seeing it. And then, as I pointed out, we do a third way, which is doing full calorimetry. I pointed out the fact that other people in the field don't measure input power the way we do, which is the way you ought to do it, voltage times current, but they subtract the thermoneutral potential, which if you put in the denominator ends up being a false positive. So here's the multiple ways that we look at excess power in parallel. We look at delta T, we look at heat flow, we look at calorimetry, and we do these other things to rule out false positives. And then I showed you for corroboration, we also look serially, where we'll take the heat energy, we'll do those 3 or 4 ways of measuring the energy at the core, and then we'll watch the heat going out. We'll measure the heat through heat flow devices, we'll put them into engines, we'll measure electricity, and I showed you some of those results. We talked about the fact that it's important to do controls. It's often laughed at in the field, but we found that we not only need thermal controls, we need dual OMA controls where we have a null calorimeter without a material in it, and then we do metallic controls. We talked about the fact that I trust no calorimeter unless I put in a square wave and it gets back a square wave, and that's why some calorimeters you shouldn't trust. I mean, they may say that they may give you a false positive or false negative, but you should always do a test and make sure you get a square wave out when you put one in. And then we talked about noise power, the fact that if you drive your system below the noise power, you're going to get a false positive. You've got to rule that out. And we talked about the fact that you can't trust certain types of calorimetry in the low flow state or when there's a vertical direction in flow calorimetry. Thermoelectrics have a weakness too. I just don't have time to go into them today. But in some conditions, unless you do a good geometric analysis where you have well-controlled flow of the heat in one direction, or where you have equal flow all the way, equal heat all the way around, they have their own problems. Then we went to day 2. We started talking about aqueous systems. When we talked about excess heat in aqueous systems by temperature, by the fact that what you always want to do is use an ohmic control here from 0 to 8 watts input power. Diffusors were giving delta T's up to 90 degrees. You could almost have coffee at that temp. And we only limited it to 100 degrees because we didn't want to boil off our $3,000 per liter heavy water, given the paucity of backing. And there's the control. So this is our power gain, incremental power gain as we drive it. Then we talked about the fact that we do thermal power spectroscopy, where we look over long periods of time. We try to measure the noise initially. We put in an ohmic control. We measure the cold fusion device at a number of levels. Here, for example, with a nickel cathode, ordinary water, and gold is the anode, we get excess energy. This is what we put in. This is what we get out. This is what we put in. This is what we get out. And we see it both for nickel with gold and nickel with platinum as the anode. And we see it with palladium as the cathode, platinum as the anode with heavy water. Here, for example, control, input, output to the controls, input, output, and yet diffusor, input, higher output, input, higher output. It's a well-calibrated system. Plus, we've done time integration so that we're able to see that with an ohmic control, you're going to get two matched slopes. And when we get excess heat, we have a superlinear rise. Questions? Okay. And we talked about the fact that often what we do, instead of switching from the ohmic control to the cold fusion device, sometimes we have two calorimeters, and then we'll have the ohmic control in one, the cold fusion device in the other. We'll switch back and forth, but we'll run them at the same time. So for example, here we have the input to the ohmic control, the output, this is the energy, here's the power, so we get a nice match. Here's the input to the cold fusion device, here's the output, and so the energy rises. The difference here is our excess energy, and we see even a heat after death where we have it down here, and when we integrate it by energy over here. And those were our aqueous systems. We talked about optimal operating point manifolds. One of the reasons that people missed cold fusion was they drove their cells in the wrong location. If the output of the device goes up and down, and we think it initially goes up for loading issues, we think it goes down because of wasteful electrolysis. When we compare the output at different drive levels, here between 0 and 8 watts, here's our excess power gain from 0 to 4 watts, we see that what we really want to do is drive it here. And then we understand the system. So we often, when we try to do our experiments with fusors and nanors, what we try to do is a evaluation mode, try to understand it, and then we do an exploitation mode. Here, for example, is another optimal operating point. This is the one we did at the open demo in Peter's office in 2003 over 5 days. And here is the same cell a year later when Brian Josephson came over. Optimal operating points. Can't get away from them, and if you don't have them, you're not going to get peak output. These are our peak outputs for a number of materials with palladium. These are the palladium nanomaterials. These are the nickel systems. We've never gotten excess heat with anything with iron or aluminum. It's very specific materials close to group 8 give us the excess heat when highly loaded. Now we talked about deuteron flux. That for me, this has been the most powerful theory because since 1989, we've made a lot of discoveries from it, and when we use it, we get excess energy. And the way that works is we look at the flow of deuterons, we divide up the flow of deuterons into what goes into the gas, what goes to fusion, tiny if we use it. I mean, we're talking like 10 to the 18th to the 20th here and 10 to the 11th or 12th here. And some of it enters the metal and some of it goes through the metal. This is what I think is causing the excess energy. When we look at the equation, we can write the flow equation for deuterium as a diffusive term and as an applied electrical energy term. This is the electric field, that's the concentration, this is the electrophoretic mobility. So this is what's moving by the applied electric field intensity. Here we have normal diffusion, that's the gradient of the concentration, times the diffusivity. Okay, so when we take that equation now, and we apply it, and apply the Einstein coefficients, and so we see then that by dividing this by D, our first order loading rate into the cathode, this is how we turn the system on, depends on two terms. One depends on the applied voltage. There's a ratio of two terms here, an ordering energy from the applied electric field and a disorder from KT. There's a geometric factor and diffusivity. So what enters the electrode is what we apply, unless thermal disorder stops it, minus what goes up in the gas, and minus what fuses, which is logical. It's a zero-sum game. The reason I think people have missed cold fusion is it's not cold fusion. It's not fusion by electrolysis, but it's one minus electrolysis. If you see electrolysis, you are wrecking your system. Two, these equations have been very successful. They led to, it's interesting, Stan Spock developed CodeDep using different equations from me, and yet we both came up with the same solution. When I applied this equation to palladium, we found that theoretically we would get a much higher loading ratio by doing CodeDep, and that's why we started doing that in '89, but stopped mainly because there was low excess energy gain. I'm trying to get higher gain so we can put it into a platform to get clean water, electricity, and propulsion like I showed you. All right, we're almost caught up. Optimal operating points, we even see it with code deposition. Here's code dep. This is when you start. This is later. This is from 0 to 12 watts. So if we're operating at 7 watts input power, here we're getting an excess energy of about 2.5 to 3 watts. Not as high as I like in terms of the ratio, but it is clear excess energy, and these are the way that you can control the systems. As you lay down the code deposition layer, we get more excess heat. We showed you that. This is break even, the zero gain here. And as we lay down more and more atoms, as what we now think are vacancies as we lay down by the code dep method, we get more excess heat. Optimal operating points are important because they're in every cold fusion system that I've looked at. And we see them for making tritium. We see them for making heat, both in palladium and nickel and with the nanomaterials. I showed you that we spent a lot of time working out the form factor for excess heat in nickel and palladium systems. That's what it looks like. This is a log input power. So we're looking at the impact of loading here. We reach a peak, and then there's the electrolysis issue. Then I showed you the propulsion systems where we put paired Stirling engines. I'm sorry. We got we've got, this is the side that was spinning. We've got the video if you want to see it. We have a cold fusion device under here. We have the ohmic control here. This is an electrical series for a smaller voltage here, less input power. We're having spinning, and here there isn't. And what we see is that there's a optimal operating point manifold as well for driving propulsion. Here we have an input power of about 6 watts. We hit our peak with a power gain just under 200%. I also pointed out to you that when you look for these optimal operating point manifolds, it turns out that when you actually go to drive a motor, it may be in a slightly different place. Then we talked about the fact that, I'll skip this. Some of these materials, when we deal with our fusors, so we take a wound coil of palladium as the cathode, we put it in heavy water that's ultra pure. So we have a solution that has an impedance, let's say 800 kiloohms, and our metal is obviously a tiny fraction compared to that. And what happens is in classical cold fusion, they'll put 2 wires in, and you get no net movement through the metal. And I think, in addition to maybe making cracks and changing the loading, etc., we change the field distribution when we do it this way. And the reason we looked at these field distributions was when we did the coils. Here's our break even. We tried all kinds of things. Here's platinum, platinum, no excess heat, iron, iron, aluminum, platinum. When finally we did a coils, and it was way higher than the others. And then we had to investigate why that worked. And that's why I think the field was a big issue. All right, let's go to some more. And I talked about the fact that when we deal with our high impedance system, and we have it actively working, we only see the bubbling on one side. And I showed before, there was a movie here, we can show it when we're done. When we have a really well done cold fusion system, maybe putting out 20 to 50 watts, we get minimal bubbling, and that's what we like to see. Questions?
When you get bubbling,
Mm.
what happens to the current? It does go down, right?
It does. The bubbling, in fact, will create a low dielectric constant layer in front of the cathode, so there's capacitive effects as well, cutting off the effective area. Yes.
It's like a polarization, right? All that will-
It's a result of the polarization, yes.
Yeah, okay.
Okay, so you see, with the wires, it doesn't matter what the distance is. You get the same effect. You get a net no flow through this. It all equals out. But we get the advantage, actually, that with these, we end up getting a flow through the metal. That's what I think is going on here. That's the current JIP. Okay. And we talked about heat after death. Fleischman and Pons reported in one of their cells that when the heavy water was all electrolyzed and empty, they were still getting excess heat, and they called it heat after death. We like to talk about tardive thermal power, which is the excess power that we get out, and when we do the time integral of that, we get heat after death. And basically here you see it, the system is shut off here, and yet, ba-bing, we still get some output, and that's heat after death. And here, for example, here we see it's above the noise level. We measure the noise here. And here's our, this is a really nice, Lou Smullen would have liked this. Lou Smullen came to watch the demo one day, and he says, you know, you've got to get that control right in the middle of the input and the output. And it's easier said than done. But I think of him anytime we pull off a perfect one here. So here you see there's a green line under here. You can barely see it. It's a nice tight match on this log scale. Yet here's to the Cold Fusion device input. Here's the output. Here's the heat after death, way above the noise level. And in this experiment, we took the heat after death and put it to work heating up a second container. So as far as I know, this was the first time that we ever used heat after death for actual work. Okay, one thing I thought was interesting was when we looked at heat after death, we saw three components. I wonder if that was the, remember when you were showing the output, by heating up metal that had the helium in it, you see the two things. I wonder if those are different sites. Just something to think about. What are we seeing? Okay. Then we talked about the fact that there's IR emission when a cold fusion system is at its active peak. And Schbach at Spire Wars had shown these flicks. I wasn't that impressed with it because there was no calibration. There was no indication this was excess heat. They hadn't done the thermometry. So we went and did it, and we got the excess heat out, and we found that for lower temperatures, we were getting more infrared out. It was a straight output of infrared, as opposed to the ohma control where we weren't seeing it. In that particular cell, the one I showed you here, we're having an energy gain of 80. Ohma control, fusor. Nice power. And we see it with nickel systems too. I don't know if you can see it across, but at the peak of the optimal operating point, it's lighting up here in the infrared. Now we talked about motor systems and the fact that we were getting gains of about 150 to 170%. We did years of this. I showed you the optimal operating point. This works for the motors as well. And remember, if you don't know what you're doing and miss it, you're not going to see the excess heat. You've got to understand your system. Otherwise, that's yet another reason for missing it. So here, for example, when we drive the Stirling engine, we see the heat after death. There's a pretty good match here between the two ohma controls. Here's our input, here's our output. And the thing I showed you was that when we start turning the engine, we lose the excess, the appearance of excess energy in the core. Remember, the way this works, it's the serial heat system. So we have a core where we're generating the excess energy. It goes through, we measure the heat flow. Sometimes we make electricity. It goes to the Stirling engine. If we actually pull the heat out, we lose the over-unity at the core because we're using it. Yes?
I have a question. What about the heat after death? How much of that is from the reaction and how much do you think is from the heat left in the middle?
Oh, I don't think it's the heat in the middle because when we look at the ohma control, which has a similar mass, maybe slightly different specific heat content, we don't see it. We only see it with the palladium.
And we don't see it with other metals. So it's clearly not involved with the heat up and the cool off of the material. This is something else. And then we talked about electricity production. It's easy to light an LED. You just put a thermoelectric against the device, but you really want to do the calibration, and even more important, you want to do the feedback loop. I talked about the fact that when we did the feedback loop, we were astonished that we were having all kinds of losses from everything. Losses from the increase in voltage from the first stage, second stage. I mean, I couldn't believe how much energy we were wasting in the switches, the wires. I guess until you really do it, it'll be interesting if ITER pulls this off in their first try. And especially the fuel cell. We had a 55% loss in the fuel cell. We won't use those anymore. Then we went to day 3. We talked about nanomaterials. By the way, I brought in one today. This is a nickel nanomaterial that we used in our Series 3 nanors that I'll be showing you. We talked about the nanomaterials, their content. The early ones were zirconium oxide. We have more advanced ones now. This is one of the earliest nanors. We use 4 terminals because I was doing 4-terminal conductivity measurements in here. When we look at the resistive ratio, well, here it's just the resistance. You take the ratio here and here to get the ratio. We find that as we keep loading, it goes up and then down, just like it does in aqueous systems. And then we talked about the fact that it's very hard to work with nanomaterials in cold fusion because you get avalanche breakdown. When you exceed a certain voltage, all of a sudden you get a massive amount of current through. Here, for example, we went above 30 volts, and we see that not only does the resistance fall, but the power dissipation goes way up as the current goes through, and it's a good way to lose your Keithley picoammeter, et cetera, et cetera. We've lost plenty. The response, here you see, for example, here's the nanomaterial before you start driving it. As you drive it, you go way down in resistance to kiloohms, and then finally it has a little bit of hysteresis, but we'll come back. I showed you Series 3 nanors. We got a little bit of excess energy. Here's the ohmic control, input, output, input, output. A little bit more out than in, which makes me happy, and especially happy if we can confirm it by heat flow measurements and calorimetry. And we started looking for materials that quench the excess heat. So for example, when we doped this with silver, we found out that's something we want to avoid, because here's our input, here's our output. And it's thermal power spectroscopy is an incredibly good way, not only of evaluating your system or configuration, but additives that you put in and how you drive it. And we talked about the Series 5 and 6 nanors. These are where we preload, and Series 6 are where we hyper preload. And so, for example, here we're looking at delta T normalized to input power. So here's our power in to the ohmic control. Here's our power in to the cold fusion device, the nanor. Here's our output. Here's our output from the nanor, and the ratio is our energy gain. And we really like it when we see not only for delta T, but we see an energy gain for heat flow, and we see an energy gain for calorimetry. So here we see the 3 together. And with calorimetry, if you want to determine your gain, you take the ratio of here to here. So one more time. If you have a delta T normalized, it's here to here. Heat flow, it's here to here to get energy gain. And calorimetry, it's here to here. And then we had Series 6 where we showed it at the course, and we had an energy gain of 14. We ran this for several months. This was, for example, the delta T as a function of input power to the control, input power to the nanor, a higher delta T to the nanor compared to the control. We divide by the input power, and what is a slope becomes a straight line. What is a slope becomes a straight line. We can take the ratio. That's why we like delta T over input power. And here, by calorimetry, we see we have a nice match of input to output and a superb 14 times gain for the nanor. Here's the nanor later. This was that evening or a day later. The thing I want you to see is the fall off. You see how there's a fall off in peak gain? You all see it? And it's regular. See how that comes? If I can do this. No, I thought there were 2 in there. There's only 1. all of them come down like this. You have either a linear or a exponential slow fall off in power. Then I showed you that some of these we can catastrophically lose the excess heat. Doesn't happen often. Maybe 1 out of every 10 man-hours that we make, and not that often. But when it happens, you fall to a gain of 1. You lose your excess energy. Okay, that was the review. Any questions?
When there is no preloading, how do the turbines get?
That's our secret. Yeah, that's our proprietary issue. And it took, anyway. We'll eventually tell. I just can't yet. Okay. You didn't get to magnetic fields at all today. I thought we were doing that.
That's slower than
Yeah.
planned.
Yikes, so.
I have auto models to kill off.
Well, there's a number of things I can talk about depending what you want. Yesterday we didn't have enough time to talk about nanomaterial transistors, impact of ultrasound. We got a lot of stuff today on magnetic fields, and so why don't I try that, and if we have more time, we'll come back to the other two if you're interested. Okay. By making nanors small and portable, we were able to do a few experiments, which I'm going to talk about now. After the demo ran here for 4 months, we tried to image the device, and we looked at the impact of magnetic fields on it. So let me go through that. You all know what magnetic fields are. You know how to induce them. If we have an electric current through a coil, we make an electric field. It has an impact on the charged particles as they move. It's a little bit more than I want to get into today. Basically, this is the setup that we had in Peter's office. It's a cartoon of what it is. We had these things close together. We have a big thermal mass around it. We're watching at the temperature rise at 3 locations in here. And it turns out we also measure the heat flow out, but you can't see it in this cartoon. We can put magnets on the top, which is what we did for DC effects. And the other thing we did is we had a circuit where we were putting electrical pulses through a coil, such that we were creating about 1.5 Tesla every 10th millisecond rise time. And then we would bring it down, repeat the pulses every few seconds. This induces approximately 40,000 volts per meter at a distance of 5 centimeters. We started initially at 80 cm, brought it closer. And so we learned a little bit about the impact of fractionated fields. And we'll talk about that in a second. These are the fields, the rate of change of the induced field. The other thing we had to do was lengthen the experiment. In Peter's office, we had run for 2-hour segments where we would do 1 hour for the control, 1 hour for the cold fusion device, and you'll see these are a little longer because we wanted to see the impact of the fields. One thing that's important is what has been the impact of magnetic fields in cold fusion before. And a number of papers have been reported where there's a small effect reported. In fact, what's also interesting is some people have reported that if there's an orthogonal field, there's actually sometimes a decrease. And this was a letter I got from Dennis Letts just before we reported it. This is Dennis's experiment, where when he goes to a certain rotation, he's able to quench it. And we found the same. We'll show you shortly. The other thing we did is in the fusor, we looked at the impact of a magnetic field. And when the field was perpendicular to the direction of the electric current, we ended up changing the impedance of the solution and the loading. And we can get into more of that later. But I believe the control of cold fusion is through the loading. So we have effects in addition to everything else we're talking about. But the loading is key. And so photoillumination has a big role. Magnetic field has a big role. And we talked about the effect on the gas. There's also an effect on the conductivity if you plug it in. And that's where this comes from. So for example, the effective loading rate depends upon the applied electric field intensity, here integrated to get the voltage, divided by the disorder. but there's a second loss term through the conductivity of the solution, and that's where we affect it. And what we think's going on is when we put on the magnetic field, this drops, and we think this increases. All right. I also mentioned that the laser irradiation we think also works that way too, but I didn't bring the graph, so I think I'll hold off. Questions?
What were your results, Mitchell?
Pardon?
What were the results with the...
Coming now. Sorry. That was materials and methods. I'm going to divide this up into two portions. I'll show the DC effect and then the AC effect. And it might not be that it's AC-DC. It may be the field intensity. We're still trying to sort it out. Okay. Constant fields. Now, remember, I showed you what the effect was. When we looked at the calorimetry of a nanor that had not seen a magnetic field, we get nice fall-offs. And so here, no H field. There's our energy gain. No H field, no H field, no H field. Well, we put on a series of magnets. And what were the results? I'll show you what the numbers are in a second. Basically, there was a slight improvement. We looked at 3 levels of fields. Then we went to a higher field. What we found is these are the 2 highest fields. That's our highest field level. We did 2 runs of each, midfield and no field. And so when we look at the energy gain as a function of applying DC fields, we do see an increase, a small effect. This was the magnets that we use are listed here. So the incremental effect is small. It's no more than 2 or so. And yet, because we're starting with an energy gain here, but we do increase it.
Mitchell,
So again,
other people might consider doubling your excess power to be a big deal.
It is, but I'm about to show you something that's bigger. It's all relative. I mean, when we applied the AC field, we went from 16 to 80.
So how strong of a field doubled the output power?
That was the big lab. I'm not sure what it was. We wrecked the detector.
On the order of a Tesla or something?
No, it's less. I now have a series of graded magnets, so we'll be able to do it, but I didn't have it then. Okay, I think the important thing is that maybe it's a large effect, but it's small compared to what I'm about to show you. And the other thing is when it's orthogonal, sometimes it inhibits it.
You see that both in palladium and in nickel?
Darn. The nanors that we have treated this way had both. I have not set up. That's a darn good question. I don't know. These were the ones that we did were zirconium oxide PDN with D.
Yeah, because the nickel is ferromagnetic, is it not?
Yes, the material is ferromagnetic once we make it.
And the palladium is not, or is it?
I'm not sure that you can. I'm not sure how to characterize a material that's an alloy and separate it out.
What are the ratio between palladium and nickel?
I showed you yesterday. If it's in here, I'll show you. Okay, we're going to talk about magnetic effects, then I'll show you the effect on CR39. Let's get the other stuff. All right. As before, we like to do a few runs without a magnetic field in the same setup. So even when we set it up to do the large AC field in that environment, we did a few runs. And what we found was that there was the same as we saw here, same effects. Then we decided that here's with the no H field, here's the ohmic control, Here's the NANR. This is after it's run about 5 or 6 months in Peter's office. So it's actually in your office, I guess it was 4 months and a month and a half on his preparation. Here was our first run. Here's our calibration pulse, OMA control, Cold Fusion device. Here's our output. This is looking at just delta T. Here's our OMA control. Here's our Cold Fusion device without the H field. So we're only putting on 1.5 Tesla, 5,000 pulses, only between here and here. So the first thing to see is it had no effect on the OMA control, which is at the identical location from the applied magnetic field intensity as the Cold Fusion device. No effect on the OMA control, and a big effect on the Cold Fusion device, and also no effect on the background, as you'll see. We saw it for the delta T, we saw it for the heat flow, and here's the calorimetry. Here's our control pulse, OMA control, Cold Fusion device, and Cold Fusion device without the field. So one thing we see is the application of a magnetic field, DC or AC, does seem to increase the output of these devices. But there's more. We went to a higher DHDT. And here we hit 0.5 Teslas by bringing it closer. And again, what we see is there's no effect on the OMA controls. There's no effect on the background, but a big effect on the Cold Fusion device itself. We see it for the delta T normalized input power, we see it for the heat flow, and we see it for the calorimetry. Here, the magnetic field is only put on between here and here, and we get a big output. I mean, this is conventional Cold Fusion. That's nothing to laugh about, but we're making it even higher. It almost looks as if this is a two-stage process. Maybe this is the first stage, and that's the second stage. We'll talk more about it in a second. The other thing I want you to look at is the peaks. Every time I've shown you peaks, they go like this, don't they? Not anymore. I don't know what's going on. Now we see rises, falls, rises. This is an active magnetic material that is producing residual effects. I use the term metachronous. It occurs after we treat it. There are synchronous effects. When we treat a material, we look and see what's going on while we treat it, and metachronous effects occurring afterwards. And we call these NANRs. After they've been treated by a magnetic field, their properties are a little different, and we say it that way. So let me show you some results. All right. These are all after we treated. So for example, here's a run where we do a series of runs. Control, NANR, control, NANR, control, NANR. And that fall off that we saw before don't exist. There's no magnetic field applied here. And yet this material is changing in time. Its activity is changing in time. I mean, I like it. It's higher than it was before it was treated. But it's not acting as it did before. There's some sort of ferroelectric or ferromagnetic or combined component in this device, or redistribution or reorganization. Something's changing, and it's changing itself as it runs. Anyway, all of them have been like this with the metachronous effects. This is an MNANR that we ran. The MNANR that we treated in June. This is February of next year. We're still getting nice output. Here's the input. This, I think this is just delta T. Yeah. Input, power, output temperature, input power, output temperature. Now there's a problem if you do these experiments. You might wreck your equipment. Coming from MIT, I didn't care too much. I do now because of the funding. But we tried orthogonal fields close, and we wrecked all kinds of equipment. And here you can see the equipment going down here. We still get excess heat out. And again, we see that with the field, we get a bigger effect compared to Cold Fusion itself. And we don't see any effect of the DHDT field on the control or in the background. This is something that is directly affecting our cold fusion system. This is a damage to the equipment. Look at that here too. Every time we see this, but look, it's going up. I'm telling you, do you have any ideas of what it is?
No, but I was going to ask you on that last one, what do you think your power gain is there?
Oh, this was, I think this might have been the 81. We had nice power gains. Here again, look at this, it's rising. I'm sorry, but this threw me away. I've been doing this for 25 years, and every time I run an experiment, it does this. And now we got something that does this, and I'm just lost. So we were twisted as to whether to keep the info for ourselves or talk. We decided to talk. This is just too big. It's very exciting. It could be a stage 2. One more issue. I thought maybe this would change the optimal operating points. This is from my lab notebook. This is what I thought would happen. We put on the magnetic field, maybe it would rise. Boy, was I wrong. This is what we got. Let me go, okay, I can't blow this up. Here's no gain. This is what we see for a resistor, 1 energy gain, okay? Here is cold fusion, this blue line. When we put on the magnetic fields, we get 2 optimal operating points. I'm telling you, we've been doing OP analysis since about '96. It's always been 1. This is the first time we've seen 2 for heat. I mean, normally we'll see multiple manifolds, 1 for tritium production, 1 for heat production. Now we see 2 for heat. So here's how we talk about them. See the peak over here? This is classical cold fusion. Goes to a peak and comes down. Okay? What happens is, after we apply the DHDT field, we get an enhancement. It goes up. And during the treatment, we get a second manifold. So the red one is during treatment, and then we stop, we go back and look over time, and what was here is now bigger. We've actually enhanced the device. We talked about this before. Here's the blow-up. Here you can see it a little better. See, here is during the treatment at one of magnetic field intensity. Here's at a higher one. And afterwards we get this. So we are changing the properties of the material. We call those M nanors. We've seen a typical 4 times increase up to 10 times increase.
And could that be residual magnetism, what you're saying?
Pardon?
Could that be as a result of residual magnetism?
Yes. I think this is not only induces a magnetic moment in there, but changes its organization, yes. So M nanors are nanors that we've activated. Now we have a way of taking nanomaterials, hyperloading them, getting them to work in a 2-terminal system, treating the device, found serendipitously, and making it even better. And to my astonishment, we got an OP manifold where we've never seen one before. Why do I think it's important? I think there may be 2 things that are allowing this to occur. I'm sure Peter disagrees. But one is clearly phonons and one might be magnons. I have no idea. I'll leave it to the smarter theoreticians. Again, if you do it, watch out for your equipment. Be careful not to destroy it. And I do think that there's a remnant magnetic moment that's induced in the material.
Did you notice the synthetic monopole announced?
No, I
Magnetic
didn't.
monopole?
No.
Anyway, magnetic field varying in time is inducing a current. So there is also dissipation of
A very large current. That 40,000 volts per meter that's induced by that field at 5 cm will induce anything. I mean, it could be as much as a milliampere per square centimeter induced based on that voltage.
And Mitchell, was the nano always running when you magnetize it, or did you also do it on a nano that was not particularly under current?
The nano was in position with the ohmic control, and both were treated for a period of time, 1 cycle.
But with electricity also going through
Yes, yes.
Have you tried it when there was no electric field, just the magnetic field as a treatment?
I think we had that in the background. I mean, when we have it hooked up, there is no heat coming out. We're putting, either in the background, it's sitting there, getting the DHDT field through it, but we don't see the heat. So I don't think it's happening then. It has to have the current going through it. Okay, so I wanted to try and see, would it make an image on CR39? Do you all know what CR39 is? It's a piece of plastic that looks like it's a film piece of plastic. And if you have ionizing penetrating radiation going through it, it leaves a track. You can put the material in 5 normal sodium hydroxide for 4 or 5 hours, and these become pits. And we built a system where we could image them. Okay, so here you're looking at the image of the pits. This was actually, what I did is we treated 3 of them. We sent them blind to Pam Boss at Spay Wars. She etched them. Then I sent them to a 3rd person to count. Though you can see for yourself, the NR's over here. You can see there's more stuff coming off here than there, even by looking at it. But let me show you the setup. So we took, here again from my lab notebook, here's where we put the nanor. We laid the CR39 over it. Here we see I've removed all the thermal material. One of the problems is when I wrap the thermal material around the nanor and the control, you can't see anything. So what we decided to do was take it out, lay everything in position, and so you're looking at the setup without the big thermal mass around it. You're just looking at where they would be if there was nothing else here, but this is normally filled up. And what we do is after we etch the pits, we have here the actual chips. We do a count. So we have essentially 4 chips we looked at. We have the control, we have a control in the chamber, we look at the whole nanor, the whole CI39 above the nanor, and we looked at this area right above the nanor. So there's 3 chips over there, and we actually do a count of 4 areas. And this is what we see for the total count, a histogram of the small and medium-sized circular pits. These are all pits and the small and mid pits, and what we found was the large pits. Let's show you what the large pits are. See these large pits? When we did large pits, they are really good for imaging. So we take account of the large pits. It turns out small, but let me show you one more thing. There's a lot of schmutz on these CI39s. So we worked out a system whereby we would eliminate the schmutz by all kinds of illumination I can't get into. But it has to do with the fact that there are ways of eliminating all the superficial problems that come on from either chemical, touching, etc. So we're looking at deep pits. And what we see is this. When we look at the large pits, we get an image. And the image is right over where the nanor was. This is what we're looking at here. This to here, this to here. And there's the nanor. So we've actually imaged it. So what does that mean? Are we putting out a lot of X-rays or just a couple? So we decided to take a look. Questions up to now? Okay. The problem is that we are radioactive. We have materials in our bodies that actually put out more gammas than the nanor. So the only way I was able to do this experiment was I built automation that ran the nanor for 3 months without us around it. And I'm going to show you those results. Basically, here was our background. In order to separate any effects, you've got to look for 2 or 3 weeks for background. And that's what we did. This may not be the best way to do it, but you see, we never got above, let's say, 16. So we set a cutoff. We set off a high-pass filter. And what we're looking at here, here's, for example, is the background of the device in position but not running. No humans around to impact it. And we can see that we don't get many hits. What's interesting is if we raise this, let's say we take our high-pass filter, we bring it up to 16 and bring it to 0, do we ever get hits more? Yes, we do. So here, for example, here is our nanor that we are allowing to run over weeks and weeks without getting near it, because you'll see that the output, we would have swamped it. And here we're measuring here's our excess energy, the ratio of these two issues, with a lot of stuff on this log scale. This is input power, this is delta T over input power, and these are our 10-minute CPMs that are above 15.5. And what we see is we have an output when we initialize the current. We get a little output when we do the nanor. We see it, and we also did it by putting a thoriated rod nearby. I was interested if the thoriated rod would increase the output of the nanor. It did not. We were still able to resolve the incremental output from the nanor, even with the thorium rod there. Here, for example, here's our excess energy. Here is these few times when we get output, but we don't get output in other regions. Now, when we plot our average of 3-minute counts as a function of input, we get this. So increased energy here for the nano. We're running at different power levels. Increased energy here, our output's here. And we see that, in fact, what's coming off does seem to be correlated to input. Now, what's really interesting is we did a time analysis. When we get the avalanches, we get output. We don't get any output from background. We get an output when we drive the nanor, and this is in that second optimal operating point. So there's a very small incremental output from nanors, but it turns out that it's on the order of 8 nanosieverts per hour watt, which is less than we have. Do we have our levels here? It's a fraction of what we each have. Here it is. Our bodies emit 46 nanosieverts per hour. So if our bodies are doing 46 per hour and our device is putting out 8.5, that's why we have to keep everybody away. And probably why other people who've tried to see it, who didn't get away, weren't able to detect that small amount. Anyway, the important issue is this has the effective emission of probably a banana peel. Potassium 40 is the biggest isotope in our environment that gives us natural background radiation. So you being in the room, you two, in fact, you in the center of the room are probably getting the highest dose right now of all these people around you. But we're used to it. Our bodies have learned how to handle background radiation. But the fact is, if you want to measure it, since you're putting out 46, you won't see it. Questions?
Do you think that will scale at nanoscales?
Boy, that's a good question. Don't know. Don't know. And also, remember, we saw a lot come out at the M point. Maybe we don't want M nanors. A lot of questions.
Have you ever measured the power dissipated by the fluctuating magnetic source?
I haven't calculated it, but it was not able to induce a temperature rise. Maybe that would give you an upper limit. That's a good question. Okay, where do we go from here? How much time we got? Are you bored yet? We can go a little more. I'm done with the magnetic fields. I can show you some of the other stuff if you want, or we can meet tomorrow. What would you like to do?
More.
More? Okay. The nanors were a successful thing we did. Not everything was that successful. Some were harder, and they didn't work as well. We tried to make transistors, and that was a lot of work, and we didn't get much. What we tried to do was build a system where it's a primitive nanor, and what we do is we're looking for ultrasound going through. So it's one-dimensional as the nanor. 2D we had ultrasound. We also added a spillover electrode to try and force more deuterium in through the side. And it was interesting. It turned out that both loadings were controlled by optimal operating points. We found out that we did get excess energy. We found out that the spillover gate did help at the core, but it was a lot of work, and we didn't get as much out as the other. We found that 2 drives were needed. We actually never made it to the other side for the resistance ratio on the spillover. All right, this is too much. I just wanted to show you this. We looked at infrared as well coming off this. So infrared, here's our control. Remember, as before, when we operate the fusors in the optimal operating point peak, we see a near infrared output. We did here too. So here, for example, here's the control. When we drive the nanors with ultrasound, we also see excess energy as well. I'll show you that in a bit. And when we drove these, it takes 3 kilovolts across here to load it. We had heat after death. We had infrared coming out during the heat after death component, and during partial operation. But the peak was when we had the whole thing driven.
What does it mean, near infrared? Near infrared means which wavelength?
These are wavelength.
So you
below red.
Filter to narrow the bandwidth.
We don't have narrow bandwidth detectors. I made these infrared detectors by cannibalizing. You know, normally when you have a cam, your cam detects infrared and visible light, and the people who manufacture it put a filter in for the infrared. So you can easily switch filters, and that's what we did. But I don't have a good characterization of the full bandwidth, which would be what you're talking about. Anyway, I'm gonna stop there. Any questions?